SAP ECC to S/4HANA migration, the silent killers nobody warns you about.
Most SAP ECC to S/4HANA migrations do not fail loudly. They fail silently. The system comes up, logins work, monitoring looks green, and yet business confidence collapses within days of go live. This video is not about how to migrate. It is about why migrations that look successful still break production.
Why Fiori, gateway and connectivity deserve special attention.
In ECC, SAP GUI was optional. In S/4HANA, Fiori is mandatory. During real migration projects, Basis teams spend nearly 40% of their time fixing Fiori, gateway, web dispatcher, OData, and connectivity issues. These problems rarely show up in sandbox or QA, but they dominate post-go-live chaos. That is why this video treats Fiori and connectivity as a first-class migration risk, not an afterthought.
How this video is structured.
This is not a tutorial and not a tool walkthrough. It is a failure reference guide. 1. Each scenario is based on real ECC to S/4HANA migration failures seen in production systems. 2. Every scenario explains what breaks, why it breaks, and why it was invisible before go live. 3. We do not show click paths, screenshots, or SAP notes walkthroughs. 4. The focus is on decision-making, architecture, and migration-specific blind spots. 5. This video is designed to be re-watched, bookmarked, and used during real projects and interviews.
The full scope, 66 migration failure scenarios.
This video covers 66 carefully selected SAP Basis migration scenarios. Each one represents a distinct failure pattern that occurs specifically during or after ECC to S/4HANA conversion. Together, they form a complete survival guide for basis consultants, technical architects, and migration leads.
Scenario categories covered in this video.
The scenarios are grouped by failure type to make patterns easy to recognize. Category 1, pre-conversion and readiness failures, 5 scenarios. Category 2, sum and shadow system failures, 5 scenarios. Category 3, work process and runtime behavior changes, 5 scenarios. Category 4, SAP HANA specific basis failures, 5 scenarios. Category 5, security and authorization migration failures, 4 scenarios. Category 6, interface and integration failures, 5 scenarios. Category 7, testing blind spots, 4 scenarios. Category 8, cutover and go-live failures, 4 scenarios. Category 9, post-go-live ghost issues, 4 scenarios. Category 10, architect-level failures, 4 scenarios. Category 11, governance and process failures, 5 scenarios. Category 12, final reality check scenarios, 6 scenarios. Category 13, Fiori, gateway and connectivity nightmares, 10 scenarios.
Category 1, pre-conversion and readiness failures.
These failures happen before the migration technically starts. They are caused by false confidence in readiness checks, underestimated prerequisites, and assumptions carried over from ECC. When these issues exist, the migration is already compromised before sum even begins.
Category 1 scenarios.
1. Migration check passes, system still fails post-conversion. 2. Unicode and kernel prerequisite gaps causing hidden runtime issues. 3. Support package and EHP mismatch leading to some phase instability. 4. Custom RFC destinations breaking after technical upgrade. 5. Archiving strategy ignored, causing conversion runtime explosion.
Scenario 1, migration check passes, system still fails after go live.
The system conversion technically succeeds. Some completes without fatal errors. Migration checks report green or acceptable warnings. Yet within hours or days of go live, users report freezes, random slowness, failed background jobs, and unpredictable behavior. From a project perspective, this is the most confusing and dangerous failure mode because nothing officially looks broken.
The real root cause.
The issue is not a failed migration. The issue is a false definition of readiness. 1. SAP migration checks validate technical compatibility, not runtime behavior under real business load. 2. They focus on static prerequisites such as Unicode, add-on compatibility, and SP levels. 3. They do not validate work process distribution, dialog-to-background balance, or HANA runtime pressure. 4. As a result, a system can be technically convertible, but operationally unfit for production usage.
Why this is a migration-exclusive failure.
This failure does not exist in normal ECC operations and appears specifically because of the migration context. 1. ECC systems evolve gradually over years, allowing basis teams to tune runtime behavior incrementally. 2. S/4HANA migration introduces a sudden and fundamental shift in database behavior, execution parallelism, and load distribution. 3. Sandbox and queue systems rarely carry full production data volume or concurrent user activity. 4. As a result, the first time the system experiences real load is often after go live, when it is already too late.
The fix, the interview-winning answer.
A senior basis consultant does not equate technical conversion with operational readiness. 1. Treat migration checks as entry criteria, not a go-live approval. 2. Validate runtime behavior under realistic load, including dialog users, background jobs, and interfaces running together. 3. Review work process distribution, instance topology, and HANA memory usage before cutover. 4. Align basis readiness checks with business execution patterns, not just SAP tooling outputs. 5. Formally sign off operational readiness as a separate milestone from technical conversion. This answer demonstrates maturity in distinguishing between technical success and business readiness.
Follow-up 1. Why do SAP migration checks give a false sense of confidence?
Answer: because they are designed to prevent technical incompatibility, not operational failure. They ensure the system can be converted, not that it will perform correctly under real usage. Migration tools cannot simulate concurrent users, background load, and business peak scenarios. Relying on them alone shifts risk directly into production.
Follow-up 2. Why didn't this issue appear during sandbox or QA testing?
Answer: sandbox and queue systems typically run with reduced data volume, fewer users, and limited job scheduling. Critical concurrency patterns, such as month-end jobs overlapping with user activity, are rarely executed. As a result, runtime stress conditions are never exercised before go live.
Follow-up 3. Curveball. Why does restarting the system temporarily improve performance?
Answer: restarting clears memory pressure, resets work process queues, and temporarily reduces contention. However, it does not fix the underlying imbalance in workload and system design. As business load returns, the same symptoms reappear, often worse than before.
Exclusive pro tip.
If a migration project cannot clearly explain how the production workload was simulated before go live, then operational readiness was never actually validated, only assumed.
Scenario 2. Unicode and kernel prerequisites met, yet runtime breaks after migration.
Before starting the ECC to S/4HANA conversion, the system meets all formal prerequisites. Unicode is enabled. The kernel is technically supported. Migration checks report no blocking issues. However, after conversion and go live, the system begins to show unpredictable runtime behavior, including short freezes, background job delays, and intermittent in-queue issues that never existed in ECC.
The real root cause.
The failure is not caused by missing prerequisites, but by treating prerequisites as sufficient conditions. 1. Unicode enablement and minimum kernel versions only guarantee technical compatibility, not stable runtime behavior. 2. Older kernel patch levels may technically support S/4HANA but contain performance or concurrency limitations. 3. Kernel behavior directly affects work process scheduling and queue handling and memory management. 4. These kernel-level inefficiencies surface only when combined with HANA execution patterns after migration.
Why this is a migration-exclusive failure?
This problem appears specifically because migration changes the execution environment abruptly. 1. ECC systems evolve gradually, allowing kernel limitations to remain hidden or be tuned over time. 2. Migration introduces a sudden shift to HANA-driven parallel execution and higher dialog throughput. 3. Kernel versions that were adequate for ECC may struggle under S/4HANA load profiles. 4. These issues rarely appear in sandbox or QA, where concurrency and load are significantly lower.
The fix, the interview-winning answer.
A senior basis consultant treats kernel and Unicode prerequisites as a baseline, not a finish line. 1. Upgrade to a stable recommended kernel patch level aligned with the target S/4HANA release. 2. Validate kernel behavior under realistic production-like load, not just technical checks. 3. Review and queue dialog and background work process behavior after kernel upgrade. 4. Align kernel planning with HANA revision strategy, not as an isolated decision. 5. Freeze kernel changes well before cutover to avoid late-stage instability. This answer shows awareness that runtime stability depends on kernel maturity, not just compatibility.
Follow-up 1. If the kernel is supported, why should we upgrade it further?
Answer: supported only means SAP allows the configuration, not that it is optimal. Later kernel patches often contain critical fixes for concurrency, memory handling, and in-queue stability that become essential on HANA. Skipping these upgrades increases the risk of unpredictable runtime issues post-migration.
Follow-up 2. Why didn't these kernel-related issues show up before migration?
Answer: ECC workloads are typically less parallel and less memory-intensive. The kernel was never stressed in the same way. S/4HANA introduces new execution patterns that expose latent kernel inefficiencies almost immediately after go-live.
Follow-up 3. Curveball. Why do some issues disappear after a kernel restart but return later?
Answer: a restart temporarily clears internal buffers, resets scheduling queues, and reduces contention. However, as load builds up again, the same kernel-level limitations resurface. This creates a misleading pattern where restarts appear to help without actually fixing the root problem.
Exclusive pro tip.
In migration projects, never ask whether a kernel version is supported. Ask whether it has proven stability on systems with similar size, load, and concurrency.
Scenario 3. Support package and EHP levels look fine. Some still becomes unstable.
Before starting the ECC to S/4HANA migration, the system appears to be on a supported support package and enhancement package level. There are no hard blockers reported by Maintenance Planner. However, during the migration, some phases take unexpectedly long, restart frequently, or behave inconsistently. Even when some completes, the resulting system shows sporadic technical issues that are difficult to correlate back to SP or EHP levels.
The real root cause.
The failure is caused by treating minimum supported SP and EHP levels as optimal baselines. 1. Support packages and enhancement packages define compatibility, not stability. 2. Some phases rely on correction instructions delivered only in later SP or kernel combinations. 3. Older SP levels may contain known issues that are tolerable in ECC but become critical during conversion. 4. This leads to unstable SUM behavior, excessive runtime, or post-conversion inconsistencies.
Why this is a migration-exclusive failure?
This issue surfaces only because migration stresses parts of the system that are rarely exercised otherwise. 1. SUM executes deep technical operations that normal ECC runtime never triggers. 2. Shadow system creation and modification logic depends heavily on stable SP or EHP combinations. 3. ECC production systems may run for years without encountering these code paths. 4. As a result, latent SP-level issues emerge only during migration.
The fix, the interview-winning answer.
A senior basis consultant aligns SP and EHP strategy with migration stability, not minimum compliance. 1. Proactively align the ECC system to a stable, recommended SP and EHP level before migration. 2. Review SAP notes and migration guides for known SUM-related SP dependencies. 3. Avoid running SUM on systems that barely meet minimum requirements. 4. Stabilize SP and EHP levels early and freeze changes well ahead of conversion. 5. Validate SUM behavior in sandbox using the exact same SP or EHP baseline planned for production. This answer demonstrates foresight in reducing migration risk through proactive system stabilization.
Follow-up 1. If the system is supported, why does SUM still behave unpredictably?
Answer: support status only guarantees SAP will allow the operation, not that it will be smooth. SUM exercises rare technical paths that may contain unresolved issues in older SPs. These paths are rarely triggered during normal ECC operations, which is why the problems surface only during migration.
Follow-up 2. Why not apply support packages during the migration itself?
Answer: applying SPs during migration increases complexity and risk. It becomes difficult to isolate whether issues are caused by some phases or by newly introduced changes. Best practice is to stabilize the system first, then migrate, rather than mixing both activities.
Follow-up 3, curveball. Why do some SP-related issues appear only after go live?
Answer: some inconsistencies are introduced during some but remain dormant until specific business processes are executed. Once real users and jobs interact with the system post-go live, these dormant issues become visible, making root cause analysis much harder.
Exclusive pro tip.
In migration projects, stability beats novelty. Always prefer a proven SP or EHP baseline over the latest available level.
Scenario 4, custom RFC connections work in ECC, break silently after migration.
After ECC to S4 HANA migration, core business processes that depend on RFC communication begin to fail intermittently. Some interfaces stop processing data, others show random delays, and a few appear to work only during off-peak hours. No obvious dumps are generated, and basic connection tests often succeed, creating confusion and delayed resolution.
The real root cause.
The issue is not RFC technology itself, but how migration alters the execution environment. 1. RFC destinations created and tuned for ECC runtime characteristics are reused without reassessment. 2. S4 HANA introduces higher parallel execution and different timing behavior for RFC calls. 3. Authorization, timeout, and resource assumptions embedded in RFC destinations become invalid. 4. As a result, RFC calls may succeed in isolation, but fail under real load.
Why this is a migration-exclusive failure?
This failure appears because migration changes system interaction patterns abruptly. 1. ECC environments often evolved gradually, allowing RFC configurations to be adjusted over time. 2. Migration introduces new execution concurrency without revalidating RFC behavior. 3. Sandbox and queue environments rarely replicate full interface traffic volume. 4. The first true stress test of RFC connectivity often occurs only after production cut over.
The fix, the interview-winning answer.
A senior basis consultant treats RFC connectivity as part of migration readiness, not post-go-live support. 1. Inventory all RFC destinations and classify them by business criticality. 2. Revalidate timeout settings, load behavior, and authorizations in the S4 HANA context. 3. Test RFCs under realistic concurrency and load, not just single-call checks. 4. Coordinate with external system owners to align expectations post-migration. 5. Document RFC behavior changes as part of the migration risk register. This answer reflects understanding that interfaces fail under load, not in isolation.
Follow-up 1. Why do RFC connection tests often succeed while real processing fails?
Answer: basic RFC tests validate connectivity and credentials, but they do not simulate concurrent calls or business load. Under real conditions, resource contention, authorization checks, and timeout thresholds behave differently, exposing weaknesses that simple tests cannot detect.
Follow-up 2. Why didn't these RFC issues exist in ECC?
Answer: ECC systems typically had lower concurrency and more predictable execution patterns. RFC destinations were tuned gradually over years. S4 HANA migration introduces a sudden shift in load and parallelism, invalidating those historical assumptions.
Follow-up 3. Curveball. Why do RFC issues often appear only during business peak hours?
Answer: peak hours amplify concurrency and resource contention. Under these conditions, RFC queues fill faster, timeouts are reached sooner, and authorization checks become more expensive. This is why problems often disappear during off-peak testing but reappear in production.
Exclusive pro tip.
Never declare RFC connectivity as working based on connection tests alone. Only load-based testing reveals migration-related interface failures.
Scenario 5. Archiving was ignored. Conversion runtime explodes unexpectedly.
The ECC system has been running for many years with minimal archiving. Business data volumes are high, but the system remains stable in daily operations. Migration checks report no hard blockers. However, during ECC to S4 HANA conversion, some runtimes increase dramatically, downtime windows are exceeded, and certain phases appear to stall or repeat without clear errors.
The real root cause.
The failure is caused by underestimating the impact of historical data volume on migration tooling. 1. Some and migration phases must process large portions of business and technical data. 2. Excessive historical data increases table sizes, index rebuild times, and data consistency checks. 3. ECC runtime stability masks the cost of carrying unnecessary historical data. 4. During migration, these costs surface abruptly as extended runtimes and downtime overruns.
Why this is a migration-exclusive failure.
This issue appears specifically because migration forces deep technical processing of existing data. 1. Normal ECC operations rarely touch the full historical dataset in a single technical process. 2. Migration requires mass table adjustments, consistency checks, and structural transformations. 3. Sandbox and queue systems often contain reduced datasets that hide the impact of data volume. 4. The true cost of unarchived data becomes visible only during conversion or cutover.
The fix, the interview-winning answer.
Senior Basis Consultant treats data volume as a technical risk, not just a storage concern. 1. Perform a thorough data volume analysis early in the migration planning phase. 2. Execute targeted archiving based on business relevance, not arbitrary retention periods. 3. Align archiving strategy with functional stakeholders well before conversion. 4. Recalculate some runtime estimates after archiving to validate downtime windows. 5. Freeze data growth during the final migration window to prevent last-minute surprises. This answer shows awareness that migration complexity scales with data volume, not just system size.
Follow-up 1. Why does excessive data not cause problems during normal ECC operations?
Answer: ECC daily operations typically access only recent and relevant data. Historical records remain largely untouched. Migration, however, requires processing entire tables, indexes, and structures, making accumulated data volume a critical factor.
Follow-up 2. Why is archiving often postponed until after migration?
Answer: archiving is sometimes seen as a business-driven activity rather than a technical necessity. Teams also fear business disruption close to migration. Unfortunately, postponing archiving shifts significant risk into the migration phase itself.
Follow-up 3. Curveball. Why can archiving after migration be more expensive?
Answer: post-migration archiving must operate on new data models, compatibility views, and HANA-optimized structures. This increases complexity and testing effort. Archiving before migration simplifies both conversion and post-go-live operations.
Exclusive pro tip.
If you cannot clearly explain how much data your migration will process, you cannot realistically estimate downtime or risk.
Category 1 recap. Readiness does not mean safety.
Every failure in this category shares a common pattern. The system was technically eligible for migration, but operationally unprepared. Prerequisites, checks, and compatibility rules prevented hard blockers, yet they failed to predict real-world behavior. When these issues exist, migration risk is already embedded long before some starts.
Why the next failures are more dangerous.
Once readiness assumptions pass unchecked, the migration moves into its most deceptive phase. The sum tool takes over, progress bars advance, and confidence rises. However, the next class of failures occurs inside the conversion engine itself, where issues are harder to diagnose and far more expensive to fix.
Category 2. Sum and shadow system failures.
These failures are unique to the migration toolchain. They occur while sum is running or immediately after it finishes. Because sum often completes successfully even when conditions are unstable, these issues create a dangerous illusion of success that collapses during cutover or shortly after go-live.
Category 2 scenarios.
6. Shadow instance competing for dialogue and background resources. 7. Sum completes successfully but system is functionally unusable. 8. Some downtime phase exceeds cutover window unexpectedly. 9. Spam and snote timing causes post-conversion inconsistencies. 10. Some restart loops due to incomplete technical cleanup.
Scenario 6. Shadow instance competes with production. Performance collapses mid-migration.
During the ECC to S4 HANA conversion, users begin reporting severe slowness and transaction freezes. even though business activity was expected to be minimal. Background jobs fall behind, dialogue response times spike, and system load appears inconsistent. From the outside, it looks like an infrastructure problem, but the timing aligns exactly with some execution.
The real root cause.
The issue is caused by unaccounted resource competition introduced by the migration process itself. 1. Some creates a shadow system that runs in parallel with the production instance. 2. The shadow instance consumes dialogue, background, memory, and CPU resources. 3. ECC era capacity planning rarely accounts for a second active system running simultaneously. 4. As a result, both systems compete for the same underlying resources, degrading performance.
Why this is a migration-exclusive failure.
This failure exists only because migration introduces a temporary but heavy parallel workload. 1. ECC operations never require a shadow system executing technical transformations. 2. Sandbox and queue migrations often run with no active users, masking resource contention. 3. Production migrations expose real user load overlapping with some activity. 4. The problem disappears after some finishes, making root cause difficult to trace.
The fix, the interview-winning answer.
A senior basis consultant plans for some as an additional system, not a background task. 1. Explicitly reserve CPU memory and work process capacity for the shadow instance. 2. Restrict or pause non-essential business activity during critical sum phases. 3. Schedule background jobs to avoid overlap with resource-intensive migration steps. 4. Monitor system behavior at the OS and HANA level, not just SAP metrics. 5. Communicate clearly to stakeholders that some execution is a controlled degradation period. This answer shows understanding that migration introduces temporary architectural stress, not just technical steps.
Follow-up 1. Why didn't we see this issue during sandbox or queue migrations?
Answer: sandbox and queue migrations usually run without real user activity or heavy background processing. Without concurrent load, the shadow system does not compete for resources. Production migrations expose this overlap for the first time.
Follow-up 2. Why does performance suddenly improve once some finishes?
Answer: once some completes, the shadow system is shut down and releases all consumed resources. This immediately reduces contention, creating the impression that the issue resolved itself. In reality, the root cause was temporary architectural overlap.
Follow-up 3. Curveball. Why can this issue cause data inconsistencies if ignored?
Answer: under extreme contention, timeouts and delayed updates can disrupt background processing and interface execution. While rare, this can lead to partial processing or retries that introduce inconsistencies, especially during cutover.
Exclusive pro tip.
Always treat the sum shadow system as a temporary second production system. If you wouldn't run two systems on the same hardware normally, don't assume migration will be safe.
Scenario 7. Sum completes successfully, but the system is functionally unusable.
The sum run finishes without fatal errors. The final phase completes, and the technical go-live checklist is marked green. However, immediately after cutover, core transactions respond slowly, background jobs queue indefinitely, and users experience timeouts across unrelated areas. From a project standpoint, this is the most dangerous moment. The migration is officially done, yet the system cannot support business operations.
The real root cause.
The failure is caused by equating some completion with runtime readiness. 1. Some validates technical consistency and completes conversion phases, not operational stability. 2. Critical post-conversion tasks such as buffer initialization, cache warming, and job rescheduling are often deferred. 3. Work process distribution and memory allocation may remain in a migration-optimized state. 4. As a result, the system starts business operation with suboptimal runtime conditions.
Why this is a migration-exclusive failure.
This failure occurs specifically because migration introduces a sharp transition from technical processing to business execution. 1. In ECC operations, system state changes gradually and buffers stabilize over time. 2. Migration forces an abrupt switch from conversion mode to full business load. 3. Sandbox and queue rarely simulate immediate post-conversion business pressure. 4. The first true operational load, often hits the system minutes after some completes.
The fix, the interview-winning answer.
A senior basis consultant treats post-sum stabilization as a mandatory phase, not an afterthought. 1. Define a formal post-sum stabilization window before allowing full business access. 2. Rebalance work processes and memory settings from migration mode to production mode. 3. Initialize and warm critical buffers before opening the system to users. 4. Restart or reschedule background jobs to avoid immediate overload. 5. Validate system behavior under controlled load before declaring business readiness. This answer demonstrates awareness that conversion success does not equal operational readiness.
Follow-up 1. Why do issues appear immediately after go-live and not during some?
Answer: during some, the system primarily performs technical operations with controlled execution patterns. Once business users and jobs are released, concurrency and load increase sharply. This sudden change exposes runtime weaknesses that were irrelevant during the conversion phases.
Follow-up 2. Why didn't monitoring tools flag these issues earlier?
Answer: monitoring during some focuses on technical progress and error states, not business response times. Key performance indicators such as dialogue response or job throughput are often ignored until users return, at which point problems become visible.
Follow-up 3. Curveball. Why does partial user access sometimes make the situation worse?
Answer: allowing a subset of users or jobs can create uneven load patterns that amplify contention. Instead of stabilizing the system, partial access introduces unpredictable concurrency, making root cause analysis harder and performance more volatile.
Exclusive pro tip.
Never announce go live at some completion. Announce it only after the system has proven stable under controlled business load.
Scenario 8. Downtime window approved. Some exceeds it without clear errors.
The business approves a fixed downtime window based on sandbox and QA runs. During production migration, some enters the downtime phase and appears to progress normally. However, the elapsed time quietly exceeds the approved window. There are no fatal errors, no obvious bottlenecks, and no single phase to blame. Yet business reopening is delayed.
The real root cause.
The failure is caused by assuming downtime behavior is linear and repeatable across systems. 1. Downtime duration is highly sensitive to data volume, table fragmentation, and index rebuild costs. 2. Production systems often contain significantly more historical and custom data than QA. 3. Certain sum phases scale non-linearly with table size and database state. 4. As a result, small differences in data characteristics produce large runtime deviations.
Why this is a migration-exclusive failure?
This issue exists because downtime phases are unique to the migration toolchain. 1. ECC operations never require exclusive locks on such a wide range of tables. 2. Sandbox and queue environments rarely mirror production data volume and fragmentation. 3. Downtime phases combine technical conversion with strict business unavailability. 4. There is no equivalent process in steady-state ECC that exposes this risk.
The fix, the interview-winning answer.
A senior basis consultant treats downtime estimation as a risk-managed forecast, not a promise. 1. Base downtime estimates on production-size data, not QA approximations. 2. Reduce data volume and fragmentation through archiving and cleanup before migration. 3. Identify and optimize long-running downtime phases using some logs and reports. 4. Communicate downtime as a range with contingency buffers, not a fixed number. 5. Prepare rollback and communication plans in case downtime exceeds expectations. This answer demonstrates realistic planning and stakeholder risk management.
Follow-up 1. Why do downtime phases scale so poorly with data size?
Answer: many downtime activities involve table locking, index rebuilds, and consistency checks. These operations do not scale linearly and are sensitive to data distribution and fragmentation. Production systems amplify these effects.
Follow-up 2. Why can't we just add more hardware to reduce downtime?
Answer: while additional resources help, some downtime activities are sequential by design. Locking and consistency checks cannot be parallelized indefinitely. Hardware reduces but does not eliminate structural limits.
Follow-up 3. Curveball. Why do repeated some restarts sometimes increase downtime?
Answer: each restart may require reinitializing phases or revalidating data states. This adds overhead and can increase total downtime. Restarts should be strategic, not reactive.
Exclusive pro tip.
If your downtime estimate has no buffer, it is not an estimate, it is a gamble.
Scenario 9. Spam and snote applied late. Post-conversion behavior becomes unpredictable.
The migration completes successfully, and the system is technically live. Shortly after go live, functional teams report inconsistent behavior. Some transactions behave differently across users, background jobs fail sporadically, and known SAP notes seem partially effective. The system appears technically stable, yet behavior is inconsistent and difficult to reproduce.
The real root cause.
The issue is caused by applying support packages and SAP notes too late in the migration timeline. 1. Spam and snote changes modify core system behavior and object definitions. 2. Applying them after conversion introduces changes that were never validated in the migrated context. 3. Some corrections interact directly with converted data structures and runtime logic. 4. This creates partial or inconsistent behavior across system components.
Why this is a migration-exclusive failure?
This failure occurs because migration freezes assumptions about system behavior. 1. During migration, system behavior is validated against a specific technical baseline. 2. Late SB or note application invalidates previously tested assumptions. 3. ECC systems tolerate late corrections more easily due to stable data models. 4. In S4 HANA, post-conversion changes interact with newly transformed structures.
The fix, the interview-winning answer.
A senior basis consultant freezes functional behavior before conversion, not after. 1. Apply required support packages and SAP notes well before starting migration. 2. Stabilize the system and complete regression testing prior to some execution. 3. Avoid functional or technical changes immediately after conversion. 4. Treat post-conversion periods as stabilization windows, not change windows. 5. Document the technical baseline used for migration and enforce it strictly. This answer reflects discipline in change control during migration.
Follow-up 1. Why do some SAP notes appear to work only partially after migration?
Answer: some notes assume pre-conversion data models or runtime behavior. When applied late, only parts of the correction align with the new system state, leading to inconsistent results that vary by transaction or user.
Follow-up 2. Why not apply critical notes immediately after go live?
Answer: applying notes immediately after go live introduces new variables during the most fragile phase. It becomes difficult to distinguish migration-related issues from newly introduced behavior, increasing resolution time and business impact.
Follow-up 3. Curveball. Why do issues sometimes disappear after reapplying the same note?
Answer: reapplication may re-trigger object regeneration or buffer resets, temporarily masking deeper inconsistencies. This creates the illusion of resolution without addressing the underlying timing problem.
Exclusive pro tip.
If a system behavior was not validated before migration, do not assume it is safe to change immediately after.
Scenario 10. Some restart loops. The same phase keeps failing without clear progress.
During the ECC to S4 HANA migration, some enters a phase that repeatedly fails or requests a restart. Each restart appears to make partial progress, but the same phase reappears with similar warnings. There are no hard errors, and logs are verbose but inconclusive. Project teams begin restarting some reactively, hoping it will eventually succeed.
The real root cause.
The failure is caused by unresolved technical prerequisites that some cannot autocorrect. 1. Some phases depend on clean technical states that must be manually corrected. 2. Restarting some without addressing the underlying issue replays the same failure conditions. 3. Log messages often describe symptoms rather than actionable causes. 4. Repeated restarts increase runtime and compound risk without improving outcomes.
Why this is a migration-exclusive failure?
This issue exists because SUM is a stateful migration engine with limited self-healing capability. 1. Normal ECC operations do not involve multi-phase, restartable technical engines. 2. SUM tracks execution state across phases, making incomplete cleanup highly impactful. 3. Sandbox runs may succeed due to cleaner technical states. 4. Production systems expose accumulated inconsistencies that some cannot resolve alone.
The fix, the interview-winning answer.
A senior basis consultant treats some restarts as diagnostic checkpoints, not retries. 1. Stop repeated restarts and analyze the failing phase in detail. 2. Correlate some logs with SAP notes specific to the phase and system release. 3. Manually resolve prerequisite issues such as inactive objects or missing authorizations. 4. Validate technical consistency before resuming some execution. 5. Document the corrective action to prevent recurrence in future runs. This answer shows controlled problem solving rather than reactive execution.
Follow-up 1. Why does some sometimes progress further after each restart?
Answer: some phases complete partial work before failing. Restarts resume from the last checkpoint, giving the illusion of progress. However, if the root issue remains unresolved, the phase will eventually fail again.
Follow-up 2. Why don't some logs clearly state what needs to be fixed?
Answer: some logs are designed for broad applicability across systems. They often report technical symptoms without deep context. Interpreting them requires experience and correlation with SAP notes and system state.
Follow-up 3. Curveball. Why can repeated restarts increase the risk of data inconsistency?
Answer: each restart may leave behind partial technical changes. Over time, these incomplete states can interact in unexpected ways, increasing the complexity of recovery and the risk of subtle inconsistencies.
Exclusive pro tip.
If you restart some more than twice without fixing anything, you are no longer migrating, you are gambling.
Category 2 recap. When the migration engine becomes the risk.
The failures in this category prove that SUM is not a background utility. It is an active, stateful system that temporarily reshapes your landscape. Shadow instances, downtime phases, late corrections, and restart loops introduce risks that do not exist in normal ECC operations. When these risks are misunderstood, technical success hides operational instability.
Why the next failures are harder to detect.
So far, failures were visible during migration execution. The next category is more dangerous because nothing technically fails. The system stays up, monitoring looks normal, yet users experience freezes, delays, and inconsistent behavior. These failures live inside runtime behavior.
Please check description or comment section of this video. I have given a lot of links for downloading 8 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem solving, generally most asked, system design, most asked implementation project-related questions and answers, support project-related questions and answers. Required for your SAP technical modules interviews jobs like SAP Basis admin jobs, SAP S4 HANA consultant jobs, SAP ABAP developer jobs, SAP ABAP OData developer jobs, SAP Fiori UE5 developer jobs, SAP ABAP HR consultant jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 8 PDFs in a single zip file from below given links.
Category 3. Work process and runtime behavior changes.
This category focuses on failures caused by changes in how work processes, dispatcher logic, update tasks, and in queue handling behave after migration. These issues are not coding problems and not database errors. They are runtime behavior shifts that invalidate years of ECC tuning assumptions.
Category 3 scenarios.
11. Dialog work process starvation after conversion. 12. Background jobs blocking dialog users post-go live. 13. In-queue behavior change after kernel and HANA switch. 14. Update task timing changes causing inconsistent business data. 15. System appears idle but users experience freezes.
Scenario 11. Dialog work process starvation after conversion.
After ECC to S/4HANA go live, users report that simple dialog transactions randomly freeze or take extremely long to respond. The system is technically up, CPU usage looks normal, and there are no dumps. Sometimes everything works smoothly, and sometimes the system feels completely blocked, especially during business peak hours.
The real root cause.
The issue is caused by an imbalance in work process utilization after migration. 1. S/4HANA shifts significant processing from the application layer to the database layer. 2. Dialog work processes spend more time waiting on database responses. 3. Background jobs and update tasks continue to consume work processes aggressively. 4. As a result, dialog work processes become starved under concurrent load.
Why this is a migration-exclusive failure.
This failure appears specifically because migration changes execution timing and load distribution. 1. ECC systems relied more heavily on application server processing with predictable execution times. 2. S/4HANA introduces longer database round trips under load due to parallel execution and locking. 3. Existing work process ratios were tuned for ECC behavior, not HANA behavior. 4. The imbalance becomes visible only when real users return after go live.
The fix, the interview-winning answer.
A senior basis consultant treats work process distribution as a migration design decision. 1. Reevaluate dialog, background, update, and spool work process ratios post-migration. 2. Analyze peak hour contention instead of average utilization. 3. Adjust background job scheduling to avoid dialog peak overlap. 4. Validate dispatcher behavior under concurrent load. 5. Retest work process distribution after every major post-go-live adjustment. This answer shows understanding that runtime balance must be redesigned for S/4HANA.
Follow-up 1. Why does CPU look normal even when users are blocked?
Answer: work process starvation is often caused by waiting states, not CPU exhaustion. Dialog processes may be waiting on database locks, update completion, or free work processes, which does not necessarily increase CPU usage.
Follow-up 2. Why didn't this issue occur in ECC?
Answer: ECC execution patterns were more sequential and predictable. Work process ratios were tuned over years. S/4HANA changes execution timing abruptly, invalidating those historical tuning assumptions.
Follow-up 3. Curveball. Why does restarting application servers temporarily fix the issue?
Answer: restarting clears work process queues and resets dispatcher state. This temporarily restores availability, but as load builds up again, the same imbalance reappears because the underlying distribution problem was never fixed.
Exclusive pro tip.
If dialog freezes disappear after an app server restart, you are dealing with a capacity balance problem, not a bug.
Scenario 12. Background jobs block dialog users after go live.
Shortly after S/4HANA go live, users report that dialog transactions freeze or take unusually long to respond during certain time windows. At the same time, background jobs appear to be running successfully. There are no dumps, no system-wide outages, and CPU usage looks acceptable. The problem appears intermittent and difficult to reproduce on demand.
The real root cause.
The issue is caused by background processing patterns that are no longer compatible with S/4HANA runtime behavior. 1. Background jobs consume work processes for longer durations after migration. 2. Database-driven processing increases wait times within each background step. 3. Legacy job scheduling assumes faster execution and shorter lock durations. 4. Under concurrent load, background jobs monopolize shared runtime resources.
Why this is a migration-exclusive failure.
This failure exists because migration changes execution timing without changing scheduling assumptions. 1. ECC background jobs were tuned based on application server-centric execution. 2. S/4HANA shifts processing to the database, altering runtime characteristics. 3. Job schedules are often migrated unchanged from ECC to S/4HANA. 4. The mismatch only becomes visible when real users and jobs run concurrently.
The fix, the interview-winning answer.
A senior basis consultant treats background job strategy as part of migration design. 1. Reclassify background jobs based on business criticality and runtime impact. 2. Reschedule heavy jobs outside dialogue peak hours after migration. 3. Limit parallel background execution during business hours. 4. Revalidate job runtimes under S/4HANA, not ECC assumptions. 5. Continuously monitor dialogue wait times during background job execution. This answer demonstrates awareness that background jobs compete with users at runtime.
Follow-up 1. Why do background jobs suddenly impact users more after migration?
Answer: S/4HANA execution increases database interaction time per job step. While total job runtime may remain acceptable, work processes are held longer. This reduces availability for dialogue users during overlapping periods.
Follow-up 2. Why didn't this happen in ECC with the same job schedule?
Answer: ECC job execution relied more heavily on application server processing with predictable runtimes. Jobs released work processes more quickly. Migration disrupts this balance without automatically adjusting schedules.
Follow-up 3. Curveball. Why does reducing dialogue users not fully resolve the issue?
Answer: the core issue is work process contention, not user count. Even with fewer users, long-running background jobs can still monopolize available processes, causing freezes whenever concurrency thresholds are crossed.
Exclusive pro tip.
After migration, job schedules should be reviewed as aggressively as custom code. Unchanged schedules are a hidden risk.
Scenario 13. NQ behavior changes after kernel and HANA switch.
After ECC to S/4HANA migration, users begin experiencing sporadic lock-related issues. Transactions hang without obvious errors, updates take longer to commit, and lock waits appear inconsistent. In some cases, business users report that saving documents feels random, sometimes instant, sometimes blocked for minutes.
The real root cause.
The issue is caused by changes in how NQ processing interacts with the database and kernel. 1. S/4HANA introduces different commit and locking behavior compared to ECC databases. 2. Kernel upgrades modify how NQ requests are processed and released. 3. Legacy assumptions about lock duration no longer hold true after migration. 4. Longer database execution times extend NQ lock lifetimes.
Why this is a migration-exclusive failure?
This failure exists because migration simultaneously changes database behavior and kernel logic. 1. ECC environments rarely experience significant variation in NQ lifetimes. 2. Migration introduces parallel execution and different commit sequencing. 3. NQ behavior remains technically correct but functionally disruptive. 4. The problem only emerges under real business concurrency after go-live.
The fix, the interview-winning answer.
A senior basis consultant treats NQ behavior as a performance characteristic, not a defect. 1. Identify transactions and jobs that hold locks for extended durations post-migration. 2. Coordinate with functional and ABAP teams to shorten lock scopes where possible. 3. Avoid scheduling high-lock jobs during dialogue peak hours. 4. Monitor NQ wait patterns rather than just lock counts. 5. Reassess NQ server sizing and configuration after migration. This answer shows understanding that lock behavior changes are systemic, not accidental.
Follow-up 1. Why do NQ waits appear random to users?
Answer: NQ waits depend on concurrency and execution timing. When database execution slows or parallelism increases, locks are held longer. From a user perspective, this appears random even though the system is behaving consistently.
Follow-up 2. Why did NQ issues appear in ECC?
Answer: ECC databases executed updates more predictably with shorter commit times. Lock durations were stable and rarely noticeable. Migration changes these timing characteristics without changing functional logic.
Follow-up 3. Curveball. Why does adding more app servers not always reduce in-queue waits?
Answer: in-queue locks are centralized. Adding application servers increases concurrency but does not reduce lock duration. In some cases, it actually increases contention and worsens the problem.
Exclusive pro tip.
If users say save feels slow now after migration, think in-queue timing before thinking performance.
Scenario 14. Update task timing changes cause inconsistent business data.
After S/4HANA go live, business users report strange data inconsistencies. Documents appear saved but related follow-up data is missing. In some cases, values appear correct initially and then change later. There are no dumps, no failed updates, and no obvious errors. The system behaves correctly most of the time, but inconsistencies appear under load.
The real root cause.
Issue is caused by changes in update task execution timing after migration. 1. Update tasks execute asynchronously and depend on system scheduling behavior. 2. S/4HANA shifts processing patterns, changing when update tasks are executed relative to dialog steps. 3. Database-driven execution introduces longer commit and wait phases under load. 4. Legacy business logic assumes update completion timing that no longer holds.
Why this is a migration-exclusive failure?
This failure exists because migration changes execution order without changing functional logic. 1. ECC execution timing was stable and predictable over many years. 2. Migration introduces new parallelism and database wait behavior. 3. Update tasks remain technically correct but execute at different moments. 4. The mismatch appears only under real post-go-live load.
The fix, the interview-winning answer.
A senior basis consultant treats update timing as a runtime contract, not an implementation detail. 1. Identify business processes that rely on immediate update completion. 2. Validate update task behavior under peak load after migration. 3. Coordinate with ABAP teams to review critical update dependencies. 4. Avoid triggering dependent logic immediately after commit work. 5. Monitor update task backlog closely during early post-go-live. This answer shows understanding that data consistency depends on execution timing, not just correctness.
Follow-up 1. Why does data appear correct and then change later?
Answer: some data is written by update tasks that execute asynchronously. Under load, these tasks may complete later than expected, causing dependent data to appear temporarily incomplete or inconsistent from a user perspective.
Follow-up 2. Why didn't this behavior exist in ECC?
Answer: ECC execution timing was more predictable, and update tasks completed quickly. Migration changes database and scheduling behavior, exposing assumptions that were never explicitly enforced.
Follow-up 3. Curveball. Why does increasing update work processes not fully fix the issue?
Answer: while additional update processes can reduce backlog, they do not change execution order or dependency assumptions. The core issue is timing expectations, not raw capacity.
Exclusive pro tip.
If users say it fixes itself after a few minutes, suspect update task timing before suspecting data corruption.
Scenario 15. System appears idle. Users experience random freezes.
After S/4HANA go live, basis monitoring dashboards show a healthy system. CPU usage is low, memory is available, and no alerts are raised. Despite this, users complain that transactions randomly freeze, screens stop responding, and sometimes recover on their own after several seconds or minutes. From an operations perspective, nothing looks wrong.
The real root cause.
The issue is caused by wait states that are invisible to traditional system monitoring. 1. Dialog work processes are blocked waiting for database responses or locks. 2. These wait states do not always consume CPU or memory resources. 3. Traditional monitoring focuses on utilization, not wait behavior. 4. As a result, the system appears idle while users are effectively blocked.
Why this is a migration-exclusive failure?
This failure occurs because migration introduces new execution patterns without changing monitoring assumptions. 1. ECC systems rarely experienced prolonged database wait states. 2. S/4HANA introduces parallel execution and longer database synchronization points. 3. Existing monitoring dashboards were designed for ECC behavior. 4. The mismatch becomes visible only after migration under real load.
The fix, the interview-winning answer.
A senior basis consultant shifts focus from utilization metrics to weight analysis. 1. Analyze dialogue response time breakdown instead of raw CPU usage. 2. Identify dominant weight types affecting dialogue work processes. 3. Correlate user complaints with runtime weight patterns. 4. Adjust workload distribution and scheduling based on weight behavior. 5. Enhance monitoring to surface weight states explicitly post-migration. This answer shows understanding that perceived slowness is often caused by weighting, not overload.
Follow-up 1. Why does the system recover without intervention?
Answer: once the blocking condition clears, such as a lock release or database synchronization, the waiting work processes resume. This creates the illusion of random freezes that resolve on their own.
Follow-up 2. Why don't CPU or memory alerts trigger during these freezes?
Answer: waiting work processes are not actively consuming resources. Since traditional alerts track utilization, not waiting, the system appears healthy even while users are blocked.
Follow-up 3. Curveball. Why does adding hardware not fix these freezes?
Answer: additional CPU or memory does not eliminate wait states caused by locks, sequencing, or synchronization points. Without addressing the underlying wait behavior, freezes persist regardless of hardware capacity.
Exclusive pro tip.
If monitoring says everything is green but users are angry, you are missing a wait state problem.
Category 3 recap. The runtime you tuned for years no longer exists.
Every failure in this category proves that S4 HANA migration is not just a technical upgrade, it is a runtime reset. Dialogue, background, update, and in-queue behavior all change simultaneously. Systems that look healthy at the infrastructure level can still fail users silently because the old ECC runtime assumptions no longer apply.
Why the next failures are even harder to control.
So far, the problems lived in the application layer. Now the failures move deeper, into the database itself. SAP HANA introduces behavior that basis teams cannot tune the same way they tuned ECC databases. These failures are subtle, systemic, and often misdiagnosed as sizing or hardware issues.
Category 4. SAP HANA-specific basis failures.
This category covers failures that exist only because SAP HANA is fundamentally different from traditional ECC databases. Memory management, parallel execution, and database-side processing behave in ways that invalidate years of basis experience. These issues often appear only after go-live, under real business load.
Category 4 scenarios.
16. HANA memory pressure appears only after migration. 17. HANA auto-unload causes random performance drops. 18. Code pushdown shifts load from app server to DB unexpectedly. 19. Parallel execution on HANA exposes legacy runtime assumptions. 20. HANA revision mismatch causes system instability.
Scenario 16. HANA memory pressure appears only after migration.
After ECC to S4 HANA go live, the system runs well initially. Over time, performance begins to degrade. HANA alerts show increasing memory usage, column store warnings appear, and some queries slow down dramatically. This happens even though memory sizing followed SAP guidelines, and no single application change explains the behavior.
The real root cause.
The issue is caused by how SAP HANA manages memory differently than ECC databases. 1. HANA keeps frequently accessed data resident in memory for performance. 2. S4 HANA data models consolidate tables, increasing column store footprint. 3. Code pushdown and parallel execution increase working set size. 4. Memory consumption grows gradually as real business patterns emerge.
Why this is a migration-exclusive failure.
This failure exists because memory behavior changes only when moving to HANA. 1. ECC databases relied on disk-based access with predictable memory usage. 2. Migration consolidates data and increases in memory residency. 3. Sandbox and QA systems rarely replicate production access patterns. 4. Memory pressure emerges only after sustained real-world usage.
The fix, the interview-winning answer.
A senior basis consultant treats HANA memory as a living resource, not a static allocation. 1. Monitor memory growth trends, not just initial consumption. 2. Identify tables and views driving the largest column store footprint. 3. Adjust unload behavior and table residency policies carefully. 4. Coordinate with ABAP teams to reduce unnecessary data access. 5. Plan memory headroom based on business growth, not just go-live size. This answer shows understanding that HANA performance depends on sustained memory health.
Follow-up 1. Why didn't memory pressure appear immediately after go-live?
Answer: HANA adapts to usage patterns over time. As business users execute reports, transactions, and batch jobs, more data remains resident in memory. This gradual accumulation delays visible pressure until weeks after go-live.
Follow-up 2. Why does adding memory sometimes fail to fix the problem?
Answer: adding memory increases capacity, but does not change inefficient access patterns. If applications continue to load excessive data into memory, consumption will grow to fill the new capacity as well.
Follow-up 3. Curveball. Why can memory pressure cause functional issues, not just slowness?
Answer: under extreme pressure, HANA may delay queries, unload tables, or throttle execution. These behaviors can cascade into timeouts and inconsistent application behavior, making memory pressure a functional risk.
Exclusive pro tip.
If HANA memory keeps growing weeks after go-live, you sized correctly, but you are operating incorrectly.
Scenario 17. HANA auto-unload causes random performance drops.
After S4 HANA go-live, users report that the system feels fast most of the time but suddenly slows down without warning. The same transaction can take 1 second in the morning and 30 seconds later in the day. There are no dumps, no short dumps, and no obvious system overload. Performance issues appear and disappear seemingly at random.
The real root cause.
The issue is caused by SAP HANA's automatic memory management behavior. 1. SAP HANA automatically unloads tables from memory when memory pressure increases. 2. Unloaded tables must be reloaded from disk when accessed again. 3. Table reload operations introduce latency that is visible to end users. 4. Auto-unload decisions are made by HANA, not by the application layer.
Why this is a migration-exclusive failure?
This failure exists only because S4 HANA relies on in-memory data residency. 1. ECC databases did not dynamically unload frequently accessed tables. 2. Migration introduces in-memory execution with active memory eviction. 3. Sandbox and queue systems rarely experience sustained memory pressure. 4. Auto-unload behavior becomes visible only in real production workloads.
The fix, the interview-winning answer.
A senior basis consultant manages memory behavior, not just memory size. 1. Identify frequently accessed tables that are being repeatedly unloaded. 2. Adjust table unload priorities for business-critical objects. 3. Review and optimize data access patterns that trigger excessive memory churn. 4. Ensure sufficient memory headroom to avoid aggressive unloading. 5. Continuously monitor unload and reload activity post-go-live. This answer demonstrates awareness that performance instability can originate inside the database.
Follow-up 1. Why does the same transaction behave differently at different times?
Answer: when required tables are already resident in memory, execution is fast. If those tables were unloaded earlier, HANA must reload them from disk, adding latency. This creates time-dependent performance behavior.
Follow-up 2. Why don't traditional performance tools show this clearly?
Answer: most tools focus on CPU and query runtime, not memory residency. Table reloads happen inside the database and are often invisible unless memory and unload metrics are explicitly monitored.
Follow-up 3. Curveball. Why can auto-unload hurt even well-written applications?
Answer: even optimized applications suffer if the database cannot keep critical data resident. Auto-unload is workload-driven, not code-driven, so good code can still experience unpredictable delays.
Exclusive pro tip.
If performance problems come and go without code changes, suspect HANA unload behavior before suspecting application defects.
Scenario 18. Code pushdown shifts load from application server to HANA unexpectedly.
After migration to S4 HANA, the system appears technically stable, but basis teams notice a fundamental shift in workload patterns. Application servers show reduced CPU usage, while the HANA database experiences sustained high CPU and memory pressure. Performance issues begin to surface even though no major infrastructure changes were made after go-live.
The real root cause.
The issue is caused by architectural workload redistribution introduced by S/4HANA. 1. S/4HANA encourages pushing data-intensive logic down to the database layer. 2. Operations previously executed in the application server now run inside HANA. 3. This fundamentally shifts CPU and memory consumption patterns. 4. Basis sizing and monitoring assumptions from ECC no longer apply.
Why this is a migration-exclusive failure.
This failure exists because migration changes where work is executed, not just how fast it runs. 1. ECC systems were designed around application server-centric processing. 2. Migration moves aggregation, filtering, and calculations into HANA. 3. Infrastructure planning often assumes similar load distribution post-migration. 4. The mismatch becomes visible only under real production workloads.
The fix, the interview-winning answer.
A senior basis consultant plans for workload relocation, not just performance tuning. 1. Reevaluate sizing assumptions for both application servers and HANA. 2. Monitor database CPU and memory as primary performance indicators. 3. Coordinate with ABAP teams on push-down-heavy scenarios. 4. Avoid assuming reduced app server load means reduced system load. 5. Design operational monitoring around the new execution architecture. This answer shows awareness that performance problems can move layers without disappearing.
Follow-up 1. Why does reduced app server CPU not mean better performance?
Answer: reduced application server load simply means work has moved elsewhere. In S/4HANA, that work is executed inside the database. If HANA becomes saturated, overall performance still degrades.
Follow-up 2. Why wasn't this visible during testing?
Answer: testing systems rarely generate the same data volume or concurrency as production. Code pushdown benefits appear positive in isolation, but cause strain only when many users and jobs run simultaneously.
Follow-up 3. Curveball. Why can adding app servers make performance worse?
Answer: more app servers increase parallel request volume sent to HANA. Without sufficient database capacity, this amplifies contention and accelerates saturation instead of improving throughput.
Exclusive pro tip.
If HANA CPU is consistently high while app servers look idle, your architecture succeeded, but your sizing did not.
Scenario 19. Parallel execution on HANA exposes legacy runtime assumptions.
After migration to S/4HANA, the system behaves unpredictably under load. Some reports complete instantly, others take far longer than expected. Batch jobs that ran sequentially in ECC now overlap in execution. Business users report inconsistent runtimes even when running the same transaction with the same input data.
The real root cause.
The issue is caused by SAP HANA executing workloads in parallel by default. 1. SAP HANA aggressively parallelizes database operations to maximize throughput. 2. Legacy ECC workloads were designed with largely sequential execution assumptions. 3. Parallel execution increases contention for shared resources such as locks and memory. 4. Runtime behavior becomes non-linear as concurrency increases.
Why this is a migration-exclusive failure?
This failure exists because parallel execution is a core characteristic of HANA, not ECC. 1. ECC databases executed most operations sequentially or with limited parallelism. 2. Migration introduces high degrees of parallel execution automatically. 3. Existing workload designs were never stress-tested for massive concurrency. 4. The issue becomes visible only when real users and jobs run simultaneously.
The fix, the interview-winning answer.
A senior basis consultant manages parallelism as a system behavior, not an anomaly. 1. Identify workloads that scale poorly under parallel execution. 2. Control job scheduling to avoid excessive concurrency peaks. 3. Coordinate with development teams to review assumptions about execution order. 4. Monitor contention indicators rather than just response times. 5. Tune system parameters with parallel execution in mind. This answer demonstrates understanding that concurrency changes system dynamics fundamentally.
Follow-up 1. Why do some runs finish instantly while others are slow?
Answer: when parallel execution paths align favorably, workloads complete quickly. Under contention, parallel tasks compete for shared resources, causing delays. This variability is inherent to parallel processing.
Follow-up 2. Why wasn't this visible in ECC performance testing?
Answer: ECC systems did not execute workloads with the same degree of parallelism. Performance testing validated sequential behavior, not concurrent execution under HANA's processing model.
Follow-up 3. Curveball. Why can limiting parallelism sometimes improve performance?
Answer: reducing parallelism lowers contention and stabilizes execution paths. While peak throughput may decrease, overall system responsiveness and predictability often improve.
Exclusive pro tip.
If performance becomes unpredictable after migration, think concurrency before thinking defects.
Scenario 20. HANA revision mismatch causes system instability.
After S/4HANA migration, the system initially appears stable. Over time, unexplained behavior starts to surface: short dumps that cannot be reproduced, inconsistent performance between application servers, and errors that disappear after system restarts. No single change explains the instability, and standard troubleshooting produces inconclusive results.
The real root cause.
The issue is caused by inconsistencies between SAP HANA revision levels and the S/4HANA application stack. 1. Different HANA revisions contain changes in query execution and memory management. 2. S/4HANA releases are certified only for specific HANA revisions. 3. Running on a non-recommended revision introduces undefined behavior. 4. Some issues appear only under certain workloads or execution paths.
Why this is a migration-exclusive failure?
This failure exists because migration introduces a tightly coupled application and database stack. 1. ECC systems tolerated a wider range of database patch levels. 2. S/4HANA relies on deep integration between application logic and HANA internals. 3. Migration often prioritizes timelines over strict revision alignment. 4. Issues emerge only after prolonged production usage.
The fix, the interview-winning answer.
A senior basis consultant treats HANA revision alignment as mandatory, not optional. 1. Verify that the HANA revision matches SAP's certified compatibility list. 2. Align HANA patching strategy with S/4HANA support packages. 3. Avoid running ahead of certified revisions in production. 4. Test critical workloads after any HANA revision change. 5. Document and enforce revision governance across landscapes. This answer shows awareness that stability depends on strict stack compatibility.
Follow-up 1. Why are these issues so hard to reproduce?
Answer: revision-related issues often depend on specific execution paths, data volumes, or timing conditions. Unless the exact conditions are replicated, the problem may not reappear, making diagnosis difficult.
Follow-up 2. Why does SAP support often ask for revision alignment first?
Answer: SAP can only analyze issues reliably on certified combinations. Misaligned revisions introduce undefined behavior that support cannot guarantee to troubleshoot accurately.
Follow-up 3. Curveball. Why can instability worsen after a seemingly minor HANA patch?
Answer: even minor revisions can change optimizer behavior or memory handling. On misaligned stacks, these changes amplify existing incompatibilities instead of fixing them.
Exclusive pro tip.
If problems vanish after a restart but return later, suspect revision mismatch before suspecting user error.
Category 4 recap. HANA is not a faster ECC database.
Every failure in this category proves one uncomfortable truth: SAP HANA changes system behavior, not just performance. Memory management, execution parallelism, and revision compatibility introduce failure modes that never existed in ECC. Treating HANA like a traditional database guarantees instability after go-live.
The next failures are invisible to basis monitoring.
So far, problems were measurable using technical metrics. The next set of failures is more dangerous because systems appear healthy while business users quietly lose access to data. These failures live in authorization models, not infrastructure dashboards.
Please check description or comment section of this video. I have given a lot of links for downloading 8 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem solving, generally most asked, system design, most asked implementation project-related questions and answers, Support project-related questions and answers. Required for your SAP technical modules interviews jobs like SAP Basis admin jobs, SAP S4 HANA consultant jobs, SAP ABAP developer jobs, SAP ABAP O data developer jobs, SAP Fiori UE5 developer jobs, SAP ABAP HR consultant jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 8 PDFs in a single zip file from below given links.
Category 5. Security and Authorization Migration Failures.
Authorization issues after S4 HANA migration are rarely technical outages. Users can log in, transactions open, and the system stays green, yet critical business data is missing or inaccessible. These failures surface only when real users attempt real work.
Category 5 Scenarios.
21. System is up, users can log in, data is missing. 22. S/4 authorization model conflicts with legacy roles. 23. RFC and background user authorizations break after conversion. 24. SAP_all masks authorization gaps until go live.
Scenario 21. System is up, users can log in, data is missing.
After S4 HANA go live, users successfully log in and launch transactions. However, reports show empty results, documents cannot be found, and business-critical data appears to be missing. From a technical perspective, the system is running perfectly, yet business operations are blocked.
The real root cause.
The issue is caused by authorization checks that did not exist or were inactive in ECC. 1. S4 HANA introduces new authorization objects and checks. 2. Legacy roles were copied forward without full redesign. 3. Data access is now filtered earlier in execution paths. 4. Missing authorizations result in empty datasets, not errors.
Why this is a migration-exclusive failure.
This failure exists because S4 HANA enforces security differently than ECC. 1. ECC allowed broader implicit access in many transactions. 2. Migration activates stricter authorization checks by default. 3. Testing often uses power users with elevated access. 4. The issue appears only when real end users log in.
The fix, the interview-winning answer.
A senior basis consultant treats authorization redesign as a migration activity, not a post-go-live fix. 1. Redesign roles based on S4 HANA authorization concepts. 2. Validate data visibility using real business users. 3. Compare SU53 outputs between ECC and S4 HANA. 4. Avoid copying roles without analysis. 5. Perform authorization testing as part of UAT. This answer demonstrates understanding that missing data can be a security issue, not a functional one.
Follow-up 1. Why are there no error messages when data is missing?
Answer: S4 HANA filters data silently based on authorization checks. Instead of throwing errors, the system simply excludes data the user is not authorized to see, making the issue harder to detect.
Follow-up 2. Why didn't this issue appear during testing?
Answer: testing is often performed by super users or consultants with broad authorizations. These users bypass the restrictions that affect actual business roles, masking the problem until go live.
Follow-up 3. Curveball. Why does SAP_all temporarily fix the issue?
Answer: SAP_all removes all authorization restrictions, allowing full data access. While this confirms the root cause, it hides real authorization gaps and creates a false sense of resolution.
Exclusive pro tip.
If users say the report runs but shows nothing, check authorizations before checking data.
Scenario 22. S/4 authorization model conflicts with legacy roles.
After S4 HANA migration, users report that transactions behave inconsistently depending on the role assigned. Some users can create documents but cannot display them later. Others can view data but fail during save. From a basis perspective, roles were transported correctly and appear identical to ECC.
The real root cause.
The issue is caused by structural changes in the S4 HANA authorization concept. 1. S4 HANA introduces new authorization objects and reorganizes existing ones. 2. Business logic is protected by more granular authorization checks. 3. Legacy ECC roles were designed around older transaction-centric models. 4. Copied roles no longer align with S4 HANA execution paths.
Why this is a migration-exclusive failure.
This failure exists because migration changes security architecture without forcing role redesign. 1. ECC roles evolved organically over many years. 2. Migration preserves role definitions without validating their relevance. 3. S4 HANA enforces authorizations deeper in the execution stack. 4. Conflicts emerge only when users execute full end-to-end processes.
The fix, the interview-winning answer.
A senior basis consultant treats role redesign as a core migration deliverable. 1. Analyze business processes instead of copying technical roles. 2. Rebuild roles using S4 HANA authorization best practices. 3. Test roles across create, change, and display scenarios. 4. Avoid overusing SAP_all or SAP_new in production. 5. Document role changes and align them with business ownership. This answer demonstrates understanding that security architecture must evolve with the system.
Follow-up 1. Why do some actions work while others fail in the same transaction?
Answer: S4 HANA performs different authorization checks at different execution stages. A user may pass initial checks but fail later when deeper business logic is executed, leading to partial functionality.
Follow-up 2. Why didn't ECC require this level of role redesign?
Answer: ECC relied on broader authorization checks and transaction-level security. S4 HANA enforces access at data and process levels, making old role designs insufficient.
Follow-up 3. Curveball. Why does adding SAP_NEW sometimes make things worse?
Answer: SAP_NEW can introduce authorizations that conflict with existing role logic. This may expose new checks while masking missing ones, increasing inconsistency rather than resolving it.
Exclusive pro tip.
If roles worked in ECC but fail in S/4 HANA, redesign, don't debug.
Scenario 23. RFC and background user authorizations break after conversion.
Immediately after S4 HANA migration, interfaces start failing and background jobs terminate unexpectedly. RFC connections that worked reliably for years now return authorization errors. From the basis perspective, users, passwords, and destinations were migrated correctly, yet automated processes stop functioning.
The real root cause.
The issue is caused by tighter authorization enforcement for technical users in S4 HANA. 1. S4 HANA introduces additional authorization checks for RFC and background execution. 2. Technical users often have minimal or outdated role assignments. 3. Some previously implicit authorizations are now explicitly required. 4. Background processing and RFC execution paths are more strictly validated.
Why this is a migration-exclusive failure?
This failure exists because migration preserves users but changes execution enforcement. 1. ECC tolerated loosely defined technical user authorizations. 2. Migration enforces stricter runtime checks without changing user design. 3. Testing often focuses on dialogue users, not technical users. 4. Failures surface immediately when automated processes resume post-go-live.
The fix, the interview-winning answer.
A senior basis consultant treats technical users as first-class migration objects. 1. Inventory all RFC and background users before migration. 2. Validate and redesign roles for technical execution in S4 HANA. 3. Test interfaces and jobs using real technical users. 4. Avoid copying dialog roles to technical users. 5. Monitor SM21 and job logs closely during early go-live. This answer demonstrates understanding that automation breaks silently without proper security alignment.
Follow-up 1. Why do these failures appear immediately after go-live?
Answer: as soon as scheduled jobs and interfaces resume, they execute under stricter authorization rules. Since no user interaction occurs, failures surface instantly without visible prompts.
Follow-up 2. Why weren't these issues detected during testing?
Answer: testing often prioritizes dialogue scenarios and business users. Technical users and background processes are frequently excluded from UAT scope, allowing authorization gaps to go unnoticed.
Follow-up 3. Curveball. Why does resetting RFC passwords not solve the issue?
Answer: password resets fix authentication problems, not authorization gaps. If required authorization objects are missing, RFC calls will continue to fail regardless of password correctness.
Exclusive pro tip.
If interfaces fail without dumps, check SU53 for technical users, not for dialogue users.
Scenario 24. SAP_all masks authorization gaps until go-live.
During migration testing, everything appears to work perfectly. Business scenarios pass, interfaces run, and users report no issues. Immediately after go-live, once SAP_all is removed from key users and support roles, critical transactions start failing and data disappears. The migration is technically complete, but business trust collapses overnight.
The real root cause.
The issue is caused by using SAP_all as a safety net instead of fixing authorization design. 1. SAP_all bypasses all authorization checks. 2. Missing or incorrect role design is never exposed during testing. 3. Authorization failures are deferred, not eliminated. 4. Go-live removes the safety net and exposes every gap at once.
Why this is a migration-exclusive failure?
This failure exists because migration compresses years of role evolution into a short timeline. 1. ECC roles evolved gradually with ongoing corrections. 2. Migration freezes role design early to meet timelines. 3. SAP_all is often used to unblock testing quickly. 4. The accumulated risk surfaces only at production cutover.
The fix, the interview-winning answer.
A senior basis consultant treats SAP_all as a diagnostic tool, not a solution. 1. Remove SAP_all from business users early in testing cycles. 2. Use SU53 and authorization trace to close gaps incrementally. 3. Validate roles with real end-to-end business scenarios. 4. Restrict SAP_all usage to controlled support users only. 5. Document and govern emergency access strictly. This answer shows understanding that security shortcuts become go-live disasters.
Follow-up 1. Why is SAP_all so dangerous during migration?
Answer: SAP_all hides authorization design flaws by allowing everything to pass. This creates a false sense of readiness. When it is removed, dozens of failures surface simultaneously, overwhelming support teams.
Follow-up 2. Why do teams keep SAP_all until go-live?
Answer: migration timelines are aggressive, and SAP_all is often used to keep testing moving. Unfortunately, this shifts the risk from testing to production, where the impact is far greater.
Follow-up 3. Curveball. Why does removing SAP_all sometimes reveal non-authorization issues?
Answer: once SAP_all is removed, execution paths change. Some logic that was previously bypassed now runs, exposing hidden configuration or process issues that were never tested under real authorization conditions.
Exclusive pro tip.
If SAP_all is still assigned during UAT, the migration is not being tested. It is being postponed.
Category 5 recap. Security failures don't break systems, they break trust.
Authorization failures after S/4HANA migration are rarely loud. The system stays up, transactions open, and monitoring looks green. Yet business users quietly lose access to data and functionality. These failures damage confidence faster than outages because they feel unpredictable and unfair to the business.
The next failures travel outside the SAP system.
So far, the failures lived inside the S/4HANA system. The next category expands the blast radius. Interfaces, middleware, and external systems begin to behave differently after migration. When these fail, the impact spreads beyond SAP into the enterprise landscape.
Category 6. Interface and integration failures.
Integration failures after S/4HANA migration are some of the most disruptive. Interfaces may still connect, queues may still move, and messages may still flow, just slower, inconsistently, or unreliably. These issues are often blamed on middleware, even when the root cause sits inside SAP.
Category 6 scenarios.
25. Inbound interfaces slow down after migration. 26. Outbound RFC queues back up post-conversion. 27. TRFC and QRFC behavior changes on HANA. 28. Middleware timeouts due to changed runtime characteristics. 29. Legacy file interfaces fail after OS or kernel change.
Scenario 25. Inbound interfaces slow down after migration.
After S/4HANA migration, inbound interfaces continue to run without errors, but throughput drops significantly. Messages arrive late, queues grow during peak hours, and downstream business processes are delayed. Middleware teams insist nothing changed on their side, while SAP monitoring shows no obvious failures.
The real root cause.
The issue is caused by changes in runtime behavior inside S/4HANA. 1. Inbound processing now triggers more database-side execution. 2. Parallel processing increases contention during peak loads. 3. Commit and update behavior differs from ECC. 4. Interfaces consume more system resources per message.
Why this is a migration-exclusive failure.
This failure exists because migration changes how SAP processes inbound work. 1. ECC inbound processing was optimized for application server execution. 2. S/4HANA shifts work closer to the database. 3. Interface volumes in testing rarely match production reality. 4. The slowdown appears only under sustained business traffic.
The fix, the interview-winning answer.
A senior basis consultant treats interfaces as performance-critical workloads. 1. Measure interface throughput before and after migration. 2. Coordinate with middleware teams on concurrency expectations. 3. Adjust scheduling and parallelism for inbound processing. 4. Monitor update and in-queue behavior during interface peaks. 5. Treat interface slowness as a system-wide performance issue. This answer shows awareness that interfaces are affected by runtime architecture, not just connectivity.
Follow-up 1. Why do inbound interfaces slow down without failing?
Answer: S/4HANA processes messages correctly but takes longer per message under load. Since no errors occur, queues grow silently, delaying business processes without triggering alerts.
Follow-up 2. Why didn't this show up during interface testing?
Answer: testing environments rarely simulate production message volume and concurrency. Performance degradation becomes visible only when sustained inbound traffic hits the system.
Follow-up 3. Curveball. Why does increasing middleware retries make things worse?
Answer: retries increase inbound load and concurrency. Instead of helping, they amplify contention inside S/4HANA, further reducing throughput.
Exclusive pro tip.
If interfaces are slow but clean, look at SAP runtime behavior, not network traces.
Scenario 26. Outbound RFC queues backup post-conversion.
After S/4HANA migration, outbound RFC destinations remain reachable and technically green. However, business teams report delays in data replication to downstream systems. SMQ1 shows growing outbound queues, and messages that once cleared in seconds now take minutes or hours. No RFC errors are logged, making the issue difficult to escalate.
The real root cause.
The issue is caused by changes in outbound processing behavior after migration. 1. Outbound RFCs now trigger more database-intensive processing steps. 2. Parallel execution increases contention during queue processing. 3. Commit and update timing changes delay queue confirmation. 4. Queue throughput decreases even though connectivity remains intact.
Why this is a migration-exclusive failure.
This failure exists because outbound RFC execution characteristics change only after migration. 1. ECC outbound RFCs relied on predictable application server execution. 2. S/4HANA shifts significant work into the database layer. 3. Queue behavior depends on commit timing that changes post-migration. 4. The backlog emerges only under sustained production traffic.
The fix, the interview-winning answer.
A senior basis consultant treats outbound queues as performance-sensitive workloads. 1. Analyze outbound queue throughput instead of connection status. 2. Balance queue parallelism to avoid database contention. 3. Coordinate with receiving systems on processing expectations. 4. Monitor update task behavior linked to RFC commits. 5. Stagger high-volume outbound jobs to reduce peak congestion. This answer shows understanding that outbound integration depends on internal execution timing.
Follow-up 1. Why do outbound queues back up without showing errors?
Answer: the system processes messages correctly but more slowly. Since no failures occur, queues simply accumulate, creating a silent delay rather than an explicit error condition.
Follow-up 2. Why didn't this behavior appear in ECC?
Answer: ECC outbound processing executed faster and more predictably. Migration introduces additional processing steps and parallel execution, altering queue dynamics.
Follow-up 3. Curveball. Why can increasing RFC queue parallelism make backlog worse?
Answer: higher parallelism increases concurrent database activity. If HANA becomes saturated, throughput drops instead of improving, causing queues to grow faster.
Exclusive pro tip.
If SMQ1 is growing but RFC destinations are green, the problem is throughput, not connectivity.
Scenario 27. TRFC and QRFC behavior changes on HANA.
After S/4HANA migration, some transactional RFCs TRFC and queued RFCs QRFC behave differently than expected. Messages are not lost, but execution order changes, retries increase, and dependent business processes slow down. Basis teams observe that queues are technically processing, yet business sequencing feels broken.
The real root cause.
The issue is caused by changes in execution timing and commit handling under SAP HANA. 1. HANA processes commits and rollbacks differently compared to ECC databases. 2. TRFC and QRFC rely heavily on commit confirmation timing. 3. Parallel execution affects queue serialization behavior. 4. Timing-sensitive sequencing assumptions no longer hold consistently.
Why this is a migration-exclusive failure.
This failure exists because RFC processing semantics change only when moving to HANA. 1. ECC databases executed commits in a more linear and predictable fashion. 2. Migration introduces parallel commit execution paths. 3. Queue logic depends on assumptions formed in ECC environments. 4. Issues appear only when multiple RFC streams run concurrently.
The fix, the interview-winning answer.
A senior basis consultant treats RFC sequencing as a runtime characteristic, not a guarantee. 1. Review and validate TRFC and QRFC processing assumptions post-migration. 2. Avoid overloading queues with excessive parallel execution. 3. Monitor commit-related delays affecting RFC confirmation. 4. Coordinate with integration teams to adjust sequencing expectations. 5. Treat RFC timing issues as architectural, not transport-level problems. This answer demonstrates awareness that reliable delivery does not always mean predictable timing.
Follow-up 1. Why are RFC messages processed but business order seems wrong?
Answer: messages are delivered correctly, but execution timing differs. When commits complete at different times, downstream systems may observe data in a different order than expected.
Follow-up 2. Why didn't ECC show this behavior?
Answer: ECC commit processing was more sequential, leading to stable ordering. Migration introduces concurrency that disrupts timing-based assumptions.
Follow-up 3. Curveball. Why does switching from TRFC to QRFC not always fix sequencing issues?
Answer: QRFC enforces order within a queue, but overall execution timing still depends on commits and resource availability. If upstream processing is unstable, QRFC alone cannot guarantee perceived business order.
Exclusive pro tip.
If interfaces are correct but out of rhythm, suspect commit timing before suspecting data corruption.
Scenario 28. Middleware timeouts due to changed runtime characteristics.
After S/4HANA migration, middleware teams begin reporting timeout errors when calling SAP services. Connections are successful, authentication works, and retries sometimes succeed. However, under peak business load, calls intermittently time out, causing message reprocessing and downstream delays. From the SAP side, no hard failures are visible.
The real root cause.
The issue is caused by longer and more variable response times inside S/4HANA. 1. S/4HANA executes more logic in the database layer. 2. Parallel execution increases response time variability. 3. Peak load conditions amplify wait states. 4. Middleware timeout thresholds remain tuned for ECC behavior.
Why this is a migration-exclusive failure.
This failure exists because migration changes response time characteristics, not connectivity. 1. ECC response times were more predictable and linear. 2. Migration introduces variability under concurrency. 3. Middleware configurations are rarely adjusted during SAP upgrades. 4. Timeouts appear only when production load ramps up.
The fix, the interview-winning answer.
A senior basis consultant treats middleware timeouts as part of migration tuning. 1. Measure real response time distributions post-migration. 2. Adjust middleware timeout thresholds based on S/4HANA behavior. 3. Reduce peak load concurrency where possible. 4. Coordinate performance tuning across SAP and middleware layers. 5. Avoid treating timeouts as network failures by default. This answer shows understanding that integration reliability depends on runtime characteristics.
Follow-up 1. Why do retries sometimes succeed?
Answer: retries often occur during lower contention windows. When load temporarily decreases, response times fall back within timeout thresholds, allowing calls to complete successfully.
Follow-up 2. Why don't SAP logs show corresponding errors?
Answer: from SAP's perspective, processing completes correctly but too slowly. Middleware aborts the call before SAP finishes, so no error is recorded on the SAP side.
Follow-up 3. Curveball. Why can increasing middleware timeout alone create new problems?
Answer: longer timeouts allow more concurrent calls to stack up, increasing load inside S/4HANA. Without balancing concurrency, this can worsen overall system responsiveness.
Exclusive pro tip.
If middleware times out but SAP finishes later, the timeout is a symptom, not the root cause.
Scenario 29. Legacy file interfaces fail after OS or kernel change.
Immediately after S/4HANA migration, legacy file-based interfaces stop working. Inbound files are no longer picked up, outbound files are not written, and some jobs fail silently. There are no syntax errors, no RFC failures, and network connectivity is intact. From a business perspective, data simply stops flowing.
The real root cause.
The issue is caused by environmental changes introduced during migration. 1. Operating system upgrades modify file system behavior and permissions. 2. Kernel upgrades enforce stricter security and access controls. 3. Legacy interfaces rely on hard-coded paths or implicit permissions. 4. File operations that worked in ECC now fail or behave differently.
Why this is a migration-exclusive failure.
This failure exists because migration often includes OS and kernel changes alongside S/4HANA. 1. ECC environments ran for years on stable OS and kernel versions. 2. Migration introduces new security defaults and execution contexts. 3. Legacy file interfaces are rarely modernized before conversion. 4. Issues appear only when production jobs resume after cutover.
The fix, the interview-winning answer.
A senior basis consultant treats file interfaces as OS-dependent components. 1. Inventory all file-based interfaces before migration. 2. Validate file paths, permissions, and execution users post-migration. 3. Avoid hard-coded directories tied to legacy environments. 4. Test inbound and outbound file jobs during cutover rehearsals. 5. Plan long-term replacement of file interfaces where possible. This answer demonstrates awareness that OS changes are part of migration risk.
Follow-up 1. Why do some file jobs fail silently?
Answer: file operations may fail due to permission or path issues without triggering ABAP dumps. Jobs complete technically but perform no meaningful work, making the failure difficult to detect.
Follow-up 2. Why didn't this happen in ECC?
Answer: ECC systems ran on long-standing OS and kernel versions with permissive defaults. Migration resets these assumptions, exposing fragile legacy configurations.
Follow-up 3. Curveball. Why can fixing permissions still not resolve the issue?
Answer: some interfaces depend on deprecated OS behavior or outdated kernel interactions. Even with correct permissions, execution context changes may require interface redesign.
Exclusive pro tip.
If files stop moving after migration, check OS and kernel changes before debugging SAP logic.
Category 6 recap. Integration issues don't break loudly, they bleed slowly.
Interface and integration failures after S/4HANA migration rarely cause immediate outages. Instead, they introduce delays, backlogs, and inconsistencies that slowly destabilize business operations. These failures are dangerous because they often get misattributed to middleware, networks, or partners, while the real cause sits inside post-migration runtime behavior.
Why none of this was seen before go live?
At this stage, a hard question must be asked. If these issues are so impactful, why were they not caught earlier? The uncomfortable answer is that migration testing often validates correctness, not reality. The next category exposes the blind spots that allow critical failures to slip through testing phases.
Please check description or comment section of this video. I have given a lot of links for downloading 8 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, system design, most asked implementation project-related questions and answers, support project-related questions and answers. Required for your SAP technical modules interviews jobs like SAP Basis admin jobs, SAP S4 HANA consultant jobs, SAP ABAP developer jobs, SAP ABAP O data developer jobs, SAP Fiori UE5 developer jobs, SAP ABAP HR consultant jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 8 PDFs in a single zip file from below given links.
Category 6 recap. Integration issues don't break loudly, they bleed slowly.
Interface and integration failures after S/4HANA migration rarely cause immediate outages. Instead, they introduce delays, backlogs, and inconsistencies that slowly destabilize business operations. These failures are dangerous because they often get misattributed to middleware, networks, or partners, while the real cause sits inside post-migration runtime behavior.
Why none of this was seen before go live?
At this stage, a hard question must be asked. If these issues are so impactful, why were they not caught earlier? The uncomfortable answer is that migration testing often validates correctness, not reality. The next category exposes the blind spots that allow critical failures to slip through testing phases.
Category 7. Testing blind spots.
Testing blind spots are the silent enablers of migration failures. Systems pass unit tests, integration tests, and even U a T, yet collapse under real-world usage. This category focuses on gaps between test environments and production reality, gaps that only become visible when real users, real data volumes, and real concurrency collide.
Category 7 Scenarios.
30. A system never reproduced production runtime issues. 31. Data volume gap masking performance problems. 32. Business scenarios not exercised during migration testing. 33. Parallel job and user load never tested pre-go live.
Scenario 30. A system never reproduced production runtime issues.
The S/4HANA system passes all testing phases successfully. A sign-off is granted, and the project moves confidently toward go live. Within days of production usage, users experience freezes, slow transactions, and intermittent timeouts, none of which were ever observed in the QA system.
The real root cause.
The issue is not a missed defect but a missing test dimension. 1. QA systems run with lower data volumes than production. 2. User concurrency in QA is a fraction of real business load. 3. Background jobs and interfaces are not stressed simultaneously. 4. Runtime contention patterns never form during testing.
Why this is a migration-exclusive failure.
This failure becomes visible only after S/4HANA migration. 1. S/4HANA introduces higher parallelism and concurrency. 2. Runtime behavior is more sensitive to data volume and load. 3. ECC systems mask these gaps with slower but steadier execution. 4. Testing assumptions formed in ECC no longer hold true.
The fix, the interview-winning answer.
A senior basis consultant aligns testing with production reality. 1. Acknowledge that QA cannot perfectly mirror production. 2. Introduce stress and concurrency testing where possible. 3. Validate system behavior under mixed workload conditions. 4. Use production monitoring patterns to guide test design. 5. Document known testing gaps as go-live risks. This answer shows maturity in understanding that testing validates assumptions, not guarantees.
Follow-up 1. Why do issues appear only after a few days in production?
Answer: problems often depend on sustained load, cache buildup, and runtime accumulation. These conditions rarely exist during short testing cycles, but emerge naturally in production.
Follow-up 2. Why not just increase QA system size?
Answer: even larger QA systems cannot replicate real user behavior, business timing, and data churn. Size alone does not recreate production dynamics.
Follow-up 3. Curveball. Why does copying production data into QA still not reproduce the issue?
Answer: data volume without production concurrency and timing patterns does not trigger the same runtime behavior. Load shape matters more than data alone.
Exclusive pro tip.
If QA looks perfect but production struggles, suspect missing load patterns, not missing fixes.
Scenario 31. Data volume gap masking performance problems.
During S/4HANA migration testing, key business transactions perform smoothly. Reports run quickly, batch jobs finish within expected time, and response times appear acceptable. After go live, the same transactions slow down dramatically, sometimes timing out under normal business usage. The functional logic is unchanged, yet performance degrades sharply.
The real root cause.
The issue is caused by a fundamental mismatch in data volume assumptions. 1. QA systems contain significantly less transactional and historical data. 2. Index usage and access paths differ at higher volumes. 3. HANA parallel execution behaves differently as table sizes grow. 4. Memory pressure and cache eviction patterns change under scale.
Why this is a migration-exclusive failure.
This failure emerges only after migrating to S/4HANA. 1. ECC databases handled large volumes with slower but predictable execution. 2. S/4HANA performance depends heavily on data distribution and size. 3. Migration often consolidates years of data into fewer tables. 4. Performance cliffs appear only beyond certain volume thresholds.
The fix, the interview-winning answer.
A senior basis consultant plans for data volume realism, not convenience. 1. Analyze production data volumes before migration. 2. Identify volume-sensitive transactions and reports. 3. Simulate large table access patterns during testing. 4. Coordinate with functional teams on data archiving strategy. 5. Treat performance validation as volume-dependent, not binary. This answer shows awareness that S/4HANA performance scales nonlinearly with data size.
Follow-up 1. Why does performance degrade suddenly instead of gradually?
Answer: S/4HANA often hits performance thresholds where execution plans change. Once these thresholds are crossed, response times can worsen rapidly rather than incrementally.
Follow-up 2. Why didn't functional testing reveal this issue?
Answer: functional testing validates correctness, not scalability. Transactions behave correctly at low volume but reveal performance weaknesses only at production scale.
Follow-up 3. Curveball. Why can archiving after go-live make things worse initially?
Answer: archiving operations themselves consume significant system resources. If not planned carefully, they add load on top of already stressed tables, worsening short-term performance.
Exclusive pro tip.
If performance is fine at low volume but collapses later, the problem is scale, not logic.
Scenario 32. Business scenarios not exercised during migration testing.
During migration testing, core business transactions are validated and signed off. After go-live, users trigger less frequent but business-critical scenarios such as period-end activities, mass updates, or exception handling processes. These scenarios fail, run extremely slowly, or behave inconsistently, despite the system passing all planned tests.
The real root cause.
The issue is caused by incomplete coverage of real business behavior. 1. Testing focuses on common daily transactions. 2. Rare but critical scenarios are excluded to save time. 3. End-to-end process chains are not fully exercised. 4. Error handling paths remain untested.
Why this is a migration-exclusive failure?
This failure becomes visible only after migration to S/4HANA. 1. S/4HANA changes execution behavior of complex scenarios. 2. Legacy ECC logic masked inefficiencies in rare processes. 3. Migration compresses timelines, reducing test scope. 4. Unexercised scenarios surface only under real business pressure.
The fix, the interview-winning answer.
A senior basis consultant treats business scenarios as runtime stress tests. 1. Identify low-frequency but high-impact business processes. 2. Include period-end and exception scenarios in testing. 3. Validate full process chains, not isolated steps. 4. Coordinate with business owners on real operational workflows. 5. Accept that limited testing scope introduces known risks. This answer demonstrates understanding that migration success depends on real business usage.
Follow-up 1. Why are these issues discovered by users and not testers?
Answer: testers follow predefined scripts. Business users trigger edge cases, shortcuts, and exception paths that were never part of formal testing cycles.
Follow-up 2. Why can't we test every business scenario?
Answer: time, data preparation, and environment constraints limit test scope. The goal is risk awareness, not total elimination.
Follow-up 3. Curveball. Why do some rare scenarios perform worse than core ones?
Answer: rare scenarios often involve complex joins, historical data, or chained updates. These stress S/4HANA differently than optimized daily transactions.
Exclusive pro tip.
If users say we don't run this often, that is exactly why you must test it.
Scenario 33. Parallel job and user load never tested pre-go live.
During migration testing, background jobs are validated, and user transactions are tested independently. After go live, both run simultaneously under real business conditions. Immediately, dialog users experience freezes, jobs miss deadlines, and overall system responsiveness degrades, even though all components pass testing individually.
The real root cause.
The issue is caused by untested contention between workloads. 1. Background jobs consume work processes and database resources. 2. Dialog users compete for the same runtime capacity. 3. HANA parallelism amplifies contention under mixed load. 4. Scheduling assumptions break when jobs and users collide.
Why this is a migration-exclusive failure?
This failure becomes visible only after S/4HANA migration. 1. ECC systems handled concurrency more conservatively. 2. S/4HANA enables higher parallel execution by default. 3. Migration increases background processing complexity. 4. Real concurrency patterns emerge only in production.
The fix, the interview-winning answer.
A senior basis consultant validates behavior under mixed workload conditions. 1. Test background jobs and dialogue usage together, not separately. 2. Identify peak business hours and critical job windows. 3. Balance work process allocation for dialogue and background. 4. Stagger heavy jobs to avoid peak user load. 5. Monitor contention indicators instead of isolated metrics. This answer demonstrates awareness that stability depends on workload interaction, not component success.
Follow-up 1. Why didn't background jobs cause issues in ECC?
Answer: ECC executed jobs more sequentially and with lower parallelism. Migration increases concurrency, making resource contention visible under real load.
Follow-up 2. Why does system monitoring still look normal?
Answer: average metrics hide short contention spikes. Users experience freezes during peaks that are smoothed out in aggregated monitoring views.
Follow-up 3. Curveball. Why does adding more dialogue work processes sometimes make performance worse?
Answer: more work processes increase concurrency and database contention. Without capacity alignment, throughput decreases instead of improving.
Exclusive pro tip.
If jobs and users were never tested together, expect surprises after go live.
Category 7 recap. Testing proved correctness, not survivability.
Category 7 exposed a hard truth. Most migration testing validates that the system works, not that it survives real business pressure. Data volume gaps, missing scenarios, and untested concurrency allow critical failures to slip through undetected. These blind spots set the stage for the most dangerous phase of all: cutover.
When there is no undo button.
Cutover marks the point where assumptions become reality. From this moment onward, every missed adjustment, incomplete activity, or rushed decision immediately impacts the business. The next category focuses on failures that occur when timelines compress and recovery options disappear.
Category 8. Cutover and go-live failures.
Cutover is not a technical event. It is an operational stress test. This category covers failures that emerge during SPDD or SPAU handling, transport sequencing, emergency fixes, and the first days of production usage. These failures are rarely caused by lack of knowledge. They are caused by lack of time.
Category 8 scenarios.
34. SPDD incomplete causing dictionary inconsistencies. 35. SPAU ignored resulting in lost custom logic. 36. Transport timing conflicts during cutover. 37. Post-go-live emergency fixes breaking system stability.
Scenario 34. SPDD incomplete causing dictionary inconsistencies.
The technical conversion completes successfully, and the system comes up after cutover. Shortly after go-live, users encounter short dumps, inconsistent table behavior, and unexplained program errors. These issues appear unrelated at first, but they all trace back to one overlooked activity during cutover.
The real root cause.
The issue is caused by incomplete SPDD adjustments during the upgrade phase. 1. Dictionary objects were modified by SAP during the upgrade. 2. Customer-specific adjustments were not fully reconciled. 3. Active versions do not match expected runtime structures. 4. Programs operate against inconsistent dictionary definitions.
Why this is a migration-exclusive failure.
This failure exists only because technical conversion changes dictionary objects. 1. ECC systems ran with stable dictionary definitions for years. 2. S4 HANA conversion introduces mandatory structural changes. 3. SPDD decisions are irreversible after go-live. 4. Issues surface only when production programs access modified objects.
The fix, the interview-winning answer.
A senior basis consultant treats SPDD as a business-critical activity. 1. Complete all SPDD adjustments before go-live. 2. Validate active dictionary versions after cutover. 3. Coordinate SPDD ownership between Basis and ABAP teams. 4. Avoid deferring SPDD decisions to post-go-live. 5. Document accepted deviations explicitly. This answer demonstrates awareness that dictionary consistency underpins system stability.
Follow-up 1. Why do SPDD issues cause seemingly unrelated dumps?
Answer: programs rely on dictionary definitions for field lengths, structures, and table layouts. When these are inconsistent, runtime errors appear in areas far removed from the original change.
Follow-up 2. Why didn't this appear during testing?
Answer: testing often uses limited scenarios and cached runtime objects. Full production usage accesses a broader set of programs and data paths, exposing inconsistencies.
Follow-up 3. Curveball. Why can fixing SPDD after go-live be riskier than before?
Answer: post-go-live SPDD changes can invalidate active programs and running transactions. Without controlled downtime, fixes can introduce new instability.
Exclusive pro tip.
If multiple unrelated issues appear after go-live, check SPDD before chasing symptoms.
Scenario 35. SBAU ignored, resulting in lost custom logic.
After go-live, business users report that certain validations, enhancements, or custom behaviors are no longer working. No dumps occur, no errors are logged, and the system appears stable. Yet key business rules that existed for years in ECC are silently missing in S/4HANA.
The real root cause.
The issue is caused by incomplete or skipped SBAU adjustments during the upgrade. 1. SAP standard programs were modified by customer logic in ECC. 2. During conversion, SAP delivered new standard versions. 3. Customer modifications were not reapplied via SBAU. 4. As a result, SAP standard overwrote custom behavior silently.
Why this is a migration-exclusive failure.
This failure exists only because migration replaces standard code. 1. ECC systems ran for years with stable modified standard programs. 2. S/4HANA conversion replaces these with new SAP-delivered logic. 3. SBAU decisions cannot be auto-merged safely. 4. Missing logic is only discovered through business usage.
The fix, the interview-winning answer.
A senior consultant treats SBAU as functional risk management. 1. Complete SBAU adjustments before go-live. 2. Involve functional teams to validate restored behavior. 3. Document which modifications are reapplied or dropped. 4. Avoid emergency SBAU fixes in production. 5. Prefer enhancements over modifications wherever possible. This answer shows understanding that lost logic is more dangerous than broken logic.
Follow-up 1. Why doesn't the system raise errors when logic is missing?
Answer: from a technical perspective, SAP standard code runs correctly. The failure is functional, not technical, making it invisible to system monitoring.
Follow-up 2. Why wasn't this caught during UAT?
Answer: UAT often focuses on happy path scenarios. Missing logic in edge cases or exception flows only appears during real business operations.
Follow-up 3. Curveball. Why is reapplying SBAU changes after go-live risky?
Answer: SBAU changes affect SAP standard programs. Applying them in production can disrupt running transactions and introduce inconsistencies without proper regression testing.
Exclusive pro tip.
If business says this used to work, check SBAU before debugging custom code.
Scenario 36. Transport timing conflicts during cut.
During cutover weekend, multiple teams move transports into the production S/4HANA system under extreme time pressure. Shortly after go-live, inconsistencies appear. Some fixes seem missing, others partially applied, and certain programs behave differently across application servers. The transport logs show no obvious failures.
The real root cause.
The issue is caused by uncontrolled transport sequencing during cutover. 1. Multiple transports target the same objects. 2. Import order is not strictly enforced. 3. Dependencies between transports are assumed, not validated. 4. Late transports overwrite earlier adjustments.
Why this is a migration-exclusive failure.
This failure exists because migration compresses months of change into hours. 1. Normal transport governance breaks down during cutover. 2. Emergency fixes bypass standard sequencing rules. 3. S/4HANA conversions introduce additional transport dependencies. 4. Errors surface only when all changes collide at once.
The fix, the interview-winning answer.
A senior consultant treats transport sequencing as a cut-over critical activity. 1. Freeze transports except for approved cut-over changes. 2. Define a strict transport import order. 3. Track object overlaps across transports. 4. Validate system state immediately after imports. 5. Assign a single transport owner during cutover. This answer demonstrates awareness that transport discipline protects system integrity.
Follow-up 1. Why do issues appear even when all transports are imported?
Answer: transport import success does not guarantee correct sequencing. Later imports can overwrite earlier changes, leaving the system in an unintended state.
Follow-up 2. Why didn't this happen in previous support packs?
Answer: routine transports are spread over time with clear ownership. Cutover compresses many changes into a short window, increasing collision risk.
Follow-up 3. Curveball. Why can re-importing transports make things worse?
Answer: repeated imports can further overwrite dependent changes, compounding inconsistencies instead of resolving them.
Exclusive pro tip.
During cutover, transport order matters more than transport count.
Scenario 37. Post-go-live emergency fixes breaking system stability.
Immediately after go-live, business pressure forces the project team to apply emergency fixes directly in production. Individual issues appear resolved, but over the next few days the system becomes increasingly unstable. New problems emerge faster than old ones are fixed, and confidence in the system drops rapidly.
The real root cause.
The issue is caused by reactive fixes applied without systemic validation. 1. Emergency transports bypass normal regression testing. 2. Fixes address symptoms instead of underlying migration issues. 3. Changes are applied under extreme time pressure. 4. System stability erodes as fixes interact unpredictably.
Why this is a migration-exclusive failure.
This failure exists because post-migration systems operate under maximum pressure. 1. Go-live issues demand immediate business resolution. 2. Rollback options are limited after conversion. 3. Multiple unresolved migration risks collide simultaneously. 4. Production becomes the first real test environment.
The fix, the interview-winning answer.
A senior consultant stabilizes before optimizing. 1. Implement a strict post-go-live change freeze. 2. Triage issues based on business impact, not urgency alone. 3. Identify and address root causes instead of symptoms. 4. Bundle fixes into controlled stabilization transports. 5. Communicate clearly with business about stabilization phases. This answer demonstrates leadership under pressure and architectural discipline.
Follow-up 1. Why do emergency fixes often create new issues?
Answer: emergency fixes are usually narrow and untested. Without understanding broader system interactions, they can destabilize unrelated areas.
Follow-up 2. Why doesn't reverting fixes restore stability?
Answer: once multiple fixes interact, reverting one change rarely restores the original state. Dependencies and side effects remain.
Follow-up 3. Curveball. Why is doing nothing sometimes the correct short-term decision?
Answer: stabilization requires observing system behavior. Pausing changes allows patterns to emerge and prevents compounding instability.
Exclusive pro tip.
After go-live, fewer fixes often lead to faster stabilization.
Category 8 recap. Go-live solves the timeline, not the risk.
Cut-over and go-live mark the end of the project plan, not the end of migration risk. Emergency fixes, transport pressure, and irreversible decisions often leave behind technical residue that does not explode immediately. Instead, it waits quietly for the system to settle before revealing itself.
When problems refuse to be reproduced.
Some of the most damaging migration failures do not appear during cut-over or immediately after go-live. They surface days or weeks later, disappear when investigated, and return without warning. These failures drain teams because they defy traditional troubleshooting.
Category 9. Post-go-live ghost issues.
Ghost issues are failures that cannot be consistently reproduced on demand. They often vanish after restarts, appear only under specific runtime conditions, and resist clear root cause analysis. This category focuses on post-migration problems that slowly erode confidence long after go-live is declared successful.
Category 9 scenarios.
38. System restart temporarily fixes issues, but why? 39. Inconsistent behavior between application servers. 40. Rare data corruption appearing weeks after go-live. 41. Performance degrades gradually after migration.
Scenario 38. System restart temporarily fixes issues, but why?
After S4 HANA go-live, users report random slowdowns, short freezes, or transaction hangs. Basis teams restart the application servers, and the problem disappears, sometimes for hours, sometimes for days. Because the restart appears to fix the issue, root cause analysis is repeatedly delayed.
The real root cause.
The restart does not resolve the issue, it resets the system state. 1. Memory fragmentation accumulates during prolonged uptime. 2. Work process distribution becomes uneven under sustained load. 3. Internal queues and caches drift out of balance. 4. Restart clears accumulated pressure without removing the cause.
Why this is a migration-exclusive failure.
This behavior becomes visible only after migrating to S/4HANA. 1. S/4HANA introduces higher concurrency and memory utilization. 2. Legacy ECC systems hid long-running imbalance more effectively. 3. Post-migration workloads differ significantly from test patterns. 4. Issues emerge only after extended production uptime.
The fix, the interview-winning answer.
A senior basis consultant treats restarts as diagnostic signals, not solutions. 1. Correlate performance issues with system uptime. 2. Monitor memory usage and work process distribution over time. 3. Identify recurring imbalance patterns before restarting. 4. Stabilize runtime behavior instead of relying on resets. 5. Document restart dependency as a production risk. This answer demonstrates maturity in separating symptom relief from root cause resolution.
Follow-up 1. Why does the system look healthy immediately after restart?
Answer: restart clears memory fragmentation, resets queues, and restores initial scheduling balance. The system appears healthy until the same runtime conditions rebuild.
Follow-up 2. Why can't this be reproduced in QA?
Answer: QA systems rarely run continuously under real production load for extended periods. The issue depends on accumulation over time, not immediate execution.
Follow-up 3. Curveball. Why do frequent restarts make the problem harder to solve?
Answer: restarts erase diagnostic evidence. By resetting system state, they prevent observation of patterns needed for true root cause analysis.
Exclusive pro tip.
If restarts fix issues, the system is telling you something, listen before resetting it.
Scenario 39. Inconsistent behavior between application servers.
After S/4HANA go live, users report that the same transaction behaves differently depending on which application server they log into. On one server, the transaction is fast and stable. On another, it is slow, times out, or behaves inconsistently. No configuration differences are visible at first glance.
The real root cause.
The issue is caused by uneven runtime state across application servers. 1. Application servers accumulate different memory and cache states over time. 2. Background jobs or user load concentrate unevenly on specific instances. 3. Runtime buffers and queues drift out of sync. 4. Server-specific contention affects execution behavior.
Why this is a migration-exclusive failure.
This behavior becomes visible primarily after migration to S/4HANA. 1. S/4HANA increases concurrency and memory sensitivity. 2. Parallel execution magnifies differences between instances. 3. Post-migration load patterns are more dynamic. 4. ECC systems mask these disparities with slower execution.
The fix, the interview-winning answer.
A senior basis consultant focuses on instance-level consistency. 1. Analyze workload distribution across application servers. 2. Balance user groups and background jobs intentionally. 3. Monitor memory, buffers, and queues per instance. 4. Identify server-specific bottlenecks instead of global averages. 5. Treat instance inconsistency as a stability risk. This answer demonstrates awareness that scale introduces variability, not uniformity.
Follow-up 1. Why does logging into a different server sometimes fix the issue?
Answer: different servers have different runtime states. Switching servers may place the user on an instance with lower contention or cleaner memory state.
Follow-up 2. Why didn't this appear before migration?
Answer: ECC systems handled load more uniformly and with lower parallelism. Migration introduces conditions where instance-level differences matter.
Follow-up 3. Curveball. Why can adding more application servers increase inconsistency?
Answer: more servers introduce more independent runtime states. Without balanced load management, variability increases instead of stabilizing.
Exclusive pro tip.
If behavior differs by server, Stop looking at system-wide averages.
Scenario 40. Rare data corruption appearing weeks after go live.
Several weeks after S/4HANA go live, business users begin reporting rare and inconsistent data issues. Financial totals occasionally do not match, document statuses appear incorrect, or historical values change unexpectedly. These issues are sporadic, difficult to reproduce, and were never observed during cutover or initial stabilization.
The real root cause.
The issue is caused by subtle runtime behavior changes interacting with legacy assumptions. 1. Legacy logic assumes sequential update timing. 2. Parallel execution on HANA changes update order. 3. Update tasks and commits interact differently post-migration. 4. Inconsistent intermediate states are written under specific timing conditions.
Why this is a migration-exclusive failure.
This issue emerges only after migration alters execution timing. 1. S/4HANA introduces high parallelism at runtime. 2. Legacy ECC systems serialized many operations implicitly. 3. Data volume and concurrency increase post-go-live. 4. Edge cases surface only under real business load.
The fix, the interview-winning answer.
A senior consultant focuses on consistency, not isolated symptoms. 1. Identify affected business objects and timing patterns. 2. Analyze update task sequencing and commit behavior. 3. Review custom logic for hidden sequential assumptions. 4. Stabilize execution paths before correcting data. 5. Involve functional teams to validate corrected outcomes. This answer demonstrates understanding of how timing affects data integrity in S/4HANA.
Follow-up 1. Why does data corruption appear weeks after go live?
Answer: the issue depends on specific timing, load, and data combinations. These conditions only occur after the system has accumulated real production usage.
Follow-up 2. Why is it so difficult to reproduce?
Answer: the corruption is timing dependent and non-deterministic. Test environments rarely recreate identical concurrency patterns.
Follow-up 3. Curveball. Why can fixing data directly make the situation worse?
Answer: manual corrections ignore the underlying timing issue. Without fixing the execution path, corruption will continue to reoccur.
Exclusive pro tip.
If corruption is rare, suspect timing, not logic.
Scenario 41. Performance degrades gradually after migration.
The system performs well immediately after S/4HANA go live. Response times are fast, users are satisfied, and monitoring dashboards look healthy. Over the next several weeks, performance slowly deteriorates. No single change or incident explains the decline, yet the system never fully recovers to its initial post-go-live state.
The real root cause.
The issue is caused by cumulative runtime and data growth effects. 1. Data volume increases rapidly after go-live. 2. Background processing intensifies under real business usage. 3. Caches, buffers, and memory usage drift over time. 4. Initial sizing assumptions no longer match production reality.
Why this is a migration-exclusive failure.
This degradation pattern is typical after major platform changes. 1. Migration resets performance baselines. 2. Test systems underestimate real data growth rates. 3. New runtime characteristics amplify small inefficiencies. 4. Problems emerge gradually instead of immediately.
The fix, the interview-winning answer.
A senior basis consultant treats performance as a lifecycle concern. 1. Establish post-go-live performance baselines. 2. Monitor trends, not isolated spikes. 3. Reevaluate sizing assumptions using real production data. 4. Optimize background processing schedules. 5. Plan iterative performance tuning cycles. This answer shows understanding that performance stability is achieved over time, not at go-live.
Follow-up 1. Why didn't performance issues appear during cutover?
Answer: cutover periods do not represent sustained production usage. Performance degradation depends on cumulative load and growth over time.
Follow-up 2. Why doesn't restarting the system permanently fix performance?
Answer: restart resets transient state, but does not address growing data volumes or inefficient processing patterns.
Follow-up 3. Curveball. Why can early success be a warning sign?
Answer: initial performance can mask future scalability issues. Early success often delays proactive tuning, until degradation becomes visible.
Exclusive pro tip.
Always treat the first month after go live as a sizing validation phase.
Category 9 recap. When the system lies quietly.
Post-go live ghost issues are the most exhausting failures in a migration. They do not crash the system, they do not leave obvious traces, and they often disappear when investigated. These issues erode trust because the system behaves unpredictably while appearing technically stable.
Beyond basis troubleshooting.
Some migration failures cannot be solved with tuning parameters, restarts, or quick fixes. They require architectural thinking, understanding how concurrency, isolation, and execution models fundamentally changed with S/4HANA.
Please check description or comment section of this video. I have given a lot of links for downloading 8 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem solving, generally most asked, system design, most asked implementation project-related questions and answers, support project-related questions and answers. Required for your SAP technical modules interviews jobs like SAP Basis admin jobs, SAP S4 HANA consultant jobs, SAP ABAP developer jobs, SAP ABAP OData developer jobs, SAP Fiori UE5 developer jobs, SAP ABAP HR consultant jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 8 PDFs in a single zip file from below given links.
Category 10. Architect level failures, rare, high impact.
These scenarios are uncommon but devastating when they occur. They sit at the intersection of database theory, runtime behavior, and legacy assumptions. Most teams struggle with them because they look like business issues, performance issues, or even user errors, when in reality, they are architectural mismatches introduced by migration.
Category 10 scenarios.
42. Snapshot isolation effects visible only on HANA. 43. Legacy timing assumptions breaking under parallelism. 44. Update task visibility issues post-migration. 45. Monitoring shows green while business is red.
Scenario 42. Snapshot isolation effects visible only on HANA.
After migration, business users report that recently saved data is sometimes not immediately visible in reports or follow-on transactions. If they retry after a short delay, the data appears. There are no update errors, no dumps, and database checks show data consistency.
The real root cause.
The issue is caused by transaction isolation behavior on SAP HANA. 1. HANA uses snapshot isolation for read operations. 2. Readers see a consistent snapshot, not uncommitted changes. 3. Parallel transactions increase visibility delays. 4. Legacy code assumes immediate read-after-write visibility.
Why this is a migration-exclusive failure.
ECC databases behave differently under concurrency. 1. ECC databases serialized many operations implicitly. 2. Snapshot isolation effects were less visible. 3. S/4HANA exposes concurrency assumptions immediately. 4. Migration changes read consistency expectations.
The fix, the interview-winning answer.
A senior architect addresses isolation, not symptoms. 1. Identify transactions affected by read-after-write assumptions. 2. Analyze commit boundaries and update task sequencing. 3. Ensure business logic does not depend on immediate visibility. 4. Refactor logic to respect transactional consistency. 5. Educate stakeholders on snapshot-based behavior. This answer demonstrates database-level architectural understanding.
Follow-up 1. Why does retrying the transaction make the data appear?
Answer: the retry occurs after the original transaction commits. The new snapshot includes the committed data, making it visible.
Follow-up 2. Why wasn't this behavior seen in ECC?
Answer: ECC databases handled isolation differently and often masked concurrency effects through serialized execution.
Follow-up 3. Curveball. Why is adding wait statements a bad fix?
Answer: artificial delays hide the problem temporarily, but introduce unpredictable performance and scalability risks.
Exclusive pro tip.
If users say it appears after refresh, suspect isolation, not missing data.
Scenario 43. Legacy timing assumptions breaking under parallelism.
After S4 HANA migration, certain business processes behave inconsistently under load. Transactions that worked reliably for years in ECC now occasionally fail, produce partial results, or trigger follow-on errors. When executed by a single user, everything works. Under parallel usage, failures appear without a clear pattern.
The real root cause.
The issue is caused by hidden timing dependencies in legacy logic. 1. Custom logic assumes sequential execution. 2. Parallel processing introduces race conditions. 3. Timing gaps expose missing synchronization. 4. Execution order is no longer predictable.
Why this is a migration-exclusive failure?
This issue appears because S4 HANA fundamentally changes execution behavior. 1. ECC systems implicitly serialized many operations. 2. S4 HANA executes logic in parallel by default. 3. Higher throughput amplifies timing assumptions. 4. Migration removes accidental synchronization.
The fix, the interview-winning answer.
A senior architect removes timing dependency instead of controlling it. 1. Identify logic relying on execution order. 2. Refactor to use explicit locking or synchronization. 3. Design processes to be order-independent. 4. Test under parallel user and job load. 5. Document concurrency assumptions explicitly. This answer demonstrates understanding of concurrency as an architectural concern.
Follow-up 1. Why does this issue disappear when tested by a single user?
Answer: single-user execution eliminates concurrency. Without parallel access, race conditions never trigger.
Follow-up 2. Why didn't stress testing catch this?
Answer: stress tests often focus on volume, not execution interleaving. Timing bugs require precise concurrency patterns.
Follow-up 3. Curveball. Why can adding in queue locks make performance worse?
Answer: locks restore correctness but reduce parallelism. Overuse can negate HANA's performance advantages.
Exclusive pro tip.
If logic depends on order, parallelism will eventually break it.
Scenario 44. Update task visibility issues post-migration.
After S4 HANA migration, users report that transactions sometimes appear to complete successfully, but related follow-on data is missing or delayed. In some cases, background reconciliation later corrects the data. There are no update termination dumps, and SM13 shows no obvious failures.
The real root cause.
The issue is caused by changed update task execution timing. 1. Update tasks are processed asynchronously. 2. Parallel execution changes commit sequencing. 3. Legacy logic assumes immediate update completion. 4. Visibility of committed data is delayed under load.
Why this is a migration-exclusive failure?
This behavior emerges due to altered runtime characteristics. 1. S4 HANA accelerates parallel update processing. 2. ECC serialized update execution more predictably. 3. Migration exposes timing gaps in legacy assumptions. 4. Higher concurrency increases visibility delays.
The fix, the interview-winning answer.
A senior architect respects asynchronous processing boundaries. 1. Identify business logic dependent on update completion. 2. Avoid immediate read-after-update assumptions. 3. Introduce explicit synchronization where required. 4. Monitor update task backlog under load. 5. Validate business processes for eventual consistency. This answer shows understanding of transactional boundaries in S4 HANA.
Follow-up 1. Why doesn't SM13 show errors?
Answer: the update tasks are not failing, they are delayed. SM13 tracks failures, not timing dependencies.
Follow-up 2. Why does data appear later without intervention?
Answer: once update tasks complete and commits finalize, the data becomes visible naturally.
Follow-up 3. Curveball. Why is forcing synchronous updates dangerous?
Answer: it reduces throughput and can cause system-wide contention, negating the benefits of parallel processing.
Exclusive pro tip.
If data arrives later, suspect asynchronous updates, not data loss.
Scenario 45. Monitoring shows green while business is red.
After S4 HANA go live, system monitoring dashboards show normal CPU, memory, and response times. From a basis perspective, the system appears healthy. However, business users report missed deadlines, delayed postings, and inconsistent processing results. There is a growing disconnect between technical metrics and business reality.
The real root cause.
The issue is caused by monitoring blind spots introduced after migration. 1. Technical monitoring focuses on infrastructure health. 2. Business process timing is not directly measured. 3. Parallel execution hides localized bottlenecks. 4. Critical delays occur within acceptable system thresholds.
Why this is a migration-exclusive failure?
This mismatch appears because S4 HANA changes performance dynamics. 1. Higher throughput masks individual transaction delays. 2. Traditional ECC monitoring was aligned with serial processing. 3. Migration introduces complexity beyond system-level KPIs. 4. Business impact decouples from raw technical metrics.
The fix, the interview-winning answer.
A senior architect aligns monitoring with business outcomes. 1. Define business-critical transaction KPIs. 2. Correlate technical metrics with process completion times. 3. Monitor end-to-end execution, not just system health. 4. Identify bottlenecks hidden within acceptable averages. 5. Treat monitoring gaps as architectural risks. This answer demonstrates maturity in aligning IT metrics with business value.
Follow-up 1. Why do standard dashboards fail to show the problem?
Answer: dashboards aggregate metrics. Localized delays and process-level bottlenecks disappear inside healthy averages.
Follow-up 2. Why wasn't this an issue in ECC?
Answer: ECC systems executed more serially, making performance issues easier to observe at system level.
Follow-up 3. Curveball. Why can adding more hardware fail to fix the issue?
Answer: hardware scaling improves capacity, not process alignment. Without business-level visibility, delays persist.
Exclusive pro tip.
If business is unhappy while metrics are green, your monitoring model is incomplete.
Category 10 recap. When the problem is the architecture.
Architect-level failures are the most misunderstood migration issues. They are rare, difficult to diagnose, and often misattributed to performance, data, or user behavior. In reality, they stem from deep mismatches between legacy assumptions and the execution model of S4 HANA.
Technology does not fail alone.
Once architectural risks are addressed, many migration failures still persist. These failures are not caused by code, configuration, or hardware. They are caused by how decisions are made, ownership is assigned, and teams operate under pressure.
Category 11. Governance and process failures.
This category focuses on failures that arise from human and organizational behavior during migration. These issues are especially dangerous because they are invisible to system monitoring and cannot be fixed with technical expertise alone.
Category 11 scenarios.
46. No single technical owner during migration. 47. Basis, ABAP, and functional teams operating in silos. 48. SAP notes applied without understanding side effects. 49. Late design changes during conversion window. 50. Overconfidence after successful sandbox conversion.
Scenario 46. No single technical owner during migration.
The migration project involves many skilled teams, Basis, ABAP, functional consultants, infrastructure, and vendors. Despite this, critical decisions are delayed, ownership is unclear, and issues bounce between teams. When problems occur, everyone is involved, yet no one is accountable.
The real root cause.
The failure is caused by fragmented ownership. 1. Responsibilities are distributed across multiple teams. 2. No single role has end-to-end technical accountability. 3. Decisions require consensus instead of authority. 4. Issues fall into gaps between domains.
Why this is a migration-exclusive failure.
Migration amplifies coordination and decision complexity. 1. Multiple technical domains change simultaneously. 2. Timelines are compressed under business pressure. 3. Legacy ownership models no longer scale. 4. Delayed decisions have irreversible consequences.
The fix, the interview-winning answer.
A senior consultant establishes clear technical ownership. 1. Assign a single end-to-end technical owner. 2. Empower that role to make binding decisions. 3. Define escalation paths clearly. 4. Align all teams under a unified technical vision. 5. Treat ownership gaps as migration risks. This answer demonstrates leadership beyond pure technical skill.
Follow-up 1. Why can't shared ownership work during migration?
Answer: shared ownership slows decisions. Migration requires fast, decisive action across domains, where delays are more damaging than imperfect decisions.
Follow-up 2. Why does this issue surface only under pressure?
Answer: in normal operations, ambiguity is manageable. Migration compresses time and risk, exposing ownership gaps immediately.
Follow-up 3. Curveball. Why can adding more experts make the problem worse?
Answer: more experts without clear authority increases debate, not resolution. Expertise without ownership creates paralysis.
Exclusive pro tip.
If everyone is responsible, no one is.
Scenario 47. Basis, ABAP, and functional teams operating in silos.
During the migration, each team focuses on its own deliverables. Basis completes the technical conversion, ABAP remediates code, and functional teams validate business processes. Despite all teams working hard, issues keep surfacing because decisions made by one group unintentionally break assumptions made by another.
The real root cause.
The failure is caused by domain isolation instead of shared accountability. 1. Teams optimize within their own scope only. 2. Technical changes are made without business context. 3. Functional requirements ignore technical constraints. 4. Cross-domain impact is discovered too late.
Why this is a migration-exclusive failure.
Migration forces simultaneous change across all layers. 1. Infrastructure, code, and business logic change together. 2. ECC allowed gradual, isolated improvements. 3. S4 HANA migration removes the buffer between domains. 4. Siloed decisions compound quickly.
The fix, the interview-winning answer.
A senior consultant enforces cross-functional ownership. 1. Establish joint decision forums across teams. 2. Validate technical changes against business scenarios. 3. Ensure functional designs consider runtime impact. 4. Create shared accountability for migration outcomes. 5. Treat silo behavior as a migration risk. This answer demonstrates understanding that migration is a system-wide transformation.
Follow-up 1. Why do siloed teams succeed in ECC but fail in migration?
Answer: ECC systems evolved slowly, allowing teams to adjust independently. Migration compresses all change into a short window, exposing disconnects immediately.
Follow-up 2. Why don't integration meetings solve this?
Answer: meetings without shared decision authority become status updates. Migration requires joint ownership, not coordination alone.
Follow-up 3. Curveball. Why can highly experienced teams still fail here?
Answer: experience within a domain does not guarantee system-level thinking. Migration demands cross-domain reasoning, not isolated expertise.
Exclusive pro tip.
If teams optimize locally, the system will fail globally.
Scenario 48. SAP notes applied without understanding side effects.
During the migration, multiple SAP notes are applied to resolve SUM errors, simplification item findings, or performance warnings. Each note appears to fix a specific problem. However, after go-live, new issues surface in unrelated areas, and teams struggle to correlate them back to the applied notes.
The real root cause.
The failure is caused by reactive SAP note application without impact analysis. 1. Notes are applied to unblock migration phases quickly. 2. Side effects on custom code or business logic are not evaluated. 3. Dependencies between notes are not fully understood. 4. Regression testing is skipped or minimized.
Why this is a migration-exclusive failure.
Migration amplifies the risk of note-related side effects. 1. Large volumes of notes are applied in a short time window. 2. Notes often modify core framework or standard behavior. 3. S/4HANA notes introduce architectural changes, not just fixes. 4. Side effects surface only under real production usage.
The fix, the interview-winning answer.
A senior consultant treats SAP notes as design changes, not patches. 1. Review the note's scope and affected components. 2. Assess impact on custom code and interfaces. 3. Apply notes in controlled batches, not ad hoc. 4. Regression test business-critical scenarios. 5. Document applied notes and observed side effects. This answer shows maturity in balancing speed with system integrity.
Follow-up 1. Why do SAP notes often cause unrelated issues?
Answer: many notes adjust shared frameworks or core logic. Changes propagate into areas not immediately obvious from the note description.
Follow-up 2. Why can't we just rely on SAP's testing?
Answer: SAP tests notes in generic scenarios. Your system's customizations and data volume create unique interaction patterns.
Follow-up 3. Curveball. Why is note-first troubleshooting dangerous?
Answer: it encourages symptom-based fixes. Without understanding root causes, teams accumulate conflicting changes that destabilize the system.
Exclusive pro tip.
Every SAP note changes behavior, even when it claims not to.
Scenario 49. Late design changes during the conversion window.
As the migration approach is cut over, new requirements or design changes are introduced. These changes are often justified as minor or necessary for go-live. Under time pressure, teams implement them directly into the conversion landscape. Shortly after go-live, stability issues emerge that were never seen in testing.
The real root cause.
The failure is caused by introducing unvalidated change during the most fragile phase. 1. Design changes bypass full regression testing. 2. Technical assumptions are not re-evaluated. 3. Dependencies with migrated components are unknown. 4. Risk assessment is replaced by urgency.
Why this is a migration-exclusive failure?
Migration creates a narrow window where change is most dangerous. 1. The system is already in a partially transformed state. 2. Baseline behavior is not yet stable. 3. Rollback options are limited after conversion. 4. Even small changes can have system-wide impact.
The fix, the interview-winning answer.
A senior consultant protects the conversion window from design volatility. 1. Freeze functional and technical design before conversion. 2. Defer non-critical changes to post-go-live phases. 3. Apply strict approval for any exception. 4. Assess impact across all migration components. 5. Communicate risk clearly to stakeholders. This answer demonstrates discipline in safeguarding system stability over scope creep.
Follow-up 1. Why are late changes more dangerous during migration?
Answer: because the system baseline is unstable. Introducing new variables prevents accurate root cause isolation.
Follow-up 2. Why do these changes often look harmless initially?
Answer: they are usually small in isolation. The risk comes from interaction with incomplete migration adjustments.
Follow-up 3. Curveball. Why can postponing changes actually accelerate go-live success?
Answer: stability allows teams to focus on fixing known issues. Adding new changes diverts attention and compounds risk.
Exclusive pro tip.
If a change is not required for go-live, it is a post-go-live change.
Scenario 50. Overconfidence after successful sandbox conversion.
The sandbox system converts successfully to S/4HANA. The technical upgrade completes, key transactions work, and early testing looks promising. Confidence grows rapidly across the project team. As a result, risk controls are relaxed, timelines are compressed, and assumptions are made that higher landscapes will behave the same way.
The real root cause.
The failure is caused by misinterpreting sandbox success as system readiness. 1. Sandbox systems have limited data volume. 2. Business usage is minimal and non-representative. 3. Interfaces and batch processing are often disabled. 4. Critical runtime characteristics are not exercised.
Why this is a migration-exclusive failure?
Migration projects amplify false confidence signals. 1. Sandbox success is often the first visible milestone. 2. Stakeholders equate technical completion with readiness. 3. Complexity increases significantly in higher landscapes. 4. Risk appetite rises prematurely.
The fix, the interview-winning answer.
A senior consultant treats sandbox conversion as a learning phase, not a proof of readiness. 1. Use sandbox results to refine conversion strategy. 2. Revalidate assumptions in development and QA. 3. Adjust timelines based on higher landscape complexity. 4. Communicate sandbox limitations clearly to stakeholders. 5. Maintain risk controls despite early success. This answer demonstrates maturity in separating technical feasibility from operational readiness.
Follow-up 1. Why does sandbox success create blind spots?
Answer: it removes perceived urgency. Teams unconsciously lower scrutiny, assuming major risks have already been eliminated.
Follow-up 2. Why do higher systems behave differently?
Answer: they carry real data volumes, full interfaces, batch workloads, and business usage patterns that sandbox systems do not.
Follow-up 3. Curveball. Why is early failure sometimes safer than early success?
Answer: early failure forces rigor and correction. Early success can hide structural weaknesses until they are expensive to fix.
Exclusive pro tip.
Sandbox success reduces technical fear, never reduce discipline.
Category 11 recap. When process failures become technical failures.
Up to this point, every failure we discussed could be traced back to governance, ownership, and decision-making under pressure. These issues do not appear in system logs, but they silently shape how migration problems are created, amplified, or ignored. If Category 11 fails, even the best technical system will struggle to survive go live.
Now comes the real battlefield.
Once governance issues collide with real users, real browsers, and real business expectations, the migration enters its most dangerous phase. This is where basis consultants spend the most time, and where credibility is either earned or permanently lost.
Please check description or comment section of this video. I have given a lot of links for downloading 8 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, system design, most asked implementation project-related questions and answers, support project-related questions and answers. Required for your SAP technical modules interviews jobs like SAP Basis admin jobs, SAP S4 HANA consultant jobs, SAP ABAP developer jobs, SAP ABAP OData developer jobs, SAP Fiori UE5 developer jobs, SAP ABAP HR consultant jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 8 PDFs in a single zip file from below given links.
Category 12. Fiori, Gateway and Connectivity Nightmares, mandatory.
In ECC, SAP GUI was king. In S4 HANA, Fiori is mandatory. This category covers the failures that do not break the backend, but completely break user trust. Nearly 40% of post-migration basis effort is spent here, not because Fiori is unstable, but because connectivity, security, and architecture assumptions change fundamentally.
Category 12 Scenarios.
51. Fiori Launchpad loads, tiles fail randomly. 52. Gateway is green, OData services fail. 53. Fiori works for some users, not others. 54. Web dispatcher routing breaks after migration. 55. S/4G UI works, Fiori is unusable. 56. Post-go-live browser cache issues masquerading as system failures. 57. HTTPS/certificate mismatches breaking Fiori access. 58. Backend is fast, Fiori is slow, why? 59. OData services time out only under load. 60. Fiori authorization issues despite SAP_all.
Scenario 51. Fiori Launchpad loads. Tiles fail randomly.
After go-live, users access the Fiori Launchpad successfully. The home page loads, groups are visible, and some tiles work. However, other tiles fail randomly with errors such as cannot open app, service not available, or endless loading spinners. Refreshing the browser sometimes fixes the issue, sometimes not.
The real root cause.
The failure is caused by inconsistent runtime resolution between front-end gateway and back-end services. 1. Multiple app components resolve through different ICF and OData paths. 2. Some services are cached while others are not. 3. Load balancer or web dispatcher routing is inconsistent. 4. Front-end and back-end systems are not perfectly aligned post-migration.
Why this is a migration-exclusive failure.
This issue appears only after migration because the UI architecture fundamentally changes. 1. ECC relied almost entirely on SAP GUI, not browser-based rendering. 2. Fiori introduces multiple layers: browser, front-end server, gateway, back-end. 3. Migration often reuses legacy routing and trust assumptions. 4. Partial activation of services creates non-deterministic behavior.
The fix, the interview-winning answer.
A senior basis consultant stabilizes Fiori by enforcing architectural consistency. 1. Validate all OData services used by failing tiles in /ilf/main_service. 2. Ensure ICF nodes are active consistently across systems. 3. Check web dispatcher routing and backend group resolution. 4. Clear and synchronize front-end and gateway caches. 5. Retest tiles under load to confirm deterministic behavior. This answer demonstrates understanding of Fiori as a distributed architecture, not a UI feature.
Follow-up 1. Why do some tiles work while others fail?
Answer: because each tile may call different OData services, ICF paths, or backend systems. Partial correctness creates the illusion of randomness.
Follow-up 2. Why does browser refresh sometimes fix the issue?
Answer: browser refresh clears client-side cache and forces a new routing decision, temporarily bypassing inconsistent backend resolution.
Follow-up 3. Curveball. Why can this issue disappear in off hours?
Answer: lower load reduces routing variance and cache contention, masking the underlying architectural inconsistency.
Exclusive pro tip.
If a Fiori issue feels random, it is almost always architectural.
Scenario 52. Gateway is green. OData services still fail.
After migration, basis checks confirm that the SAP gateway system is up and running. System health checks are green, ICM is active, and no dumps are visible. However, Fiori apps fail with OData errors such as HTTP 500, service not found, or metadata load failures. From a monitoring perspective, everything looks normal.
The real root cause.
The failure is caused by a disconnect between gateway runtime status and OData service readiness. 1. Gateway core services are active, but specific OData services are inactive or misconfigured. 2. Service activation was incomplete during migration or post-processing. 3. Backend alias or system alias mapping is incorrect. 4. Authorizations for technical OData users are missing or inconsistent.
Why this is a migration-exclusive failure.
This issue appears because migration introduces gateway as a critical runtime layer. 1. ECC systems did not rely on OData-based UI consumption. 2. Gateway activation is often new or expanded during S/4HANA migration. 3. Technical aliases and trust relationships are recreated, not upgraded. 4. Green system status does not validate service-level readiness.
The fix, the interview-winning answer.
A senior basis consultant validates gateway functionality at the service level, not the system level. 1. Verify failing services in /ilf/main_service. 2. Check backend system alias configuration and RFC destinations. 3. Test OData metadata and service calls directly. 4. Validate authorizations for gateway technical users. 5. Re-register and reactivate affected OData services. This answer demonstrates that gateway health is defined by service execution, not green status indicators.
Follow-up 1. Why does gateway monitoring show green while apps fail?
Answer: because monitoring checks core processes, not individual OData service activation or backend connectivity.
Follow-up 2. Why does this issue often affect only some apps?
Answer: different apps consume different services. Partial activation leads to selective failure.
Follow-up 3. Curveball. Why can restarting gateway temporarily fix the issue?
Answer: restart clears caches and reloads service metadata, masking misconfiguration until the next cache rebuild.
Exclusive pro tip.
Green gateway means nothing unless OData works end-to-end.
Scenario 53. Fiori works for some users, not others.
After go live, a confusing pattern emerges. Some users can access Fiori apps without any issues, while others receive authorization errors, blank screens, or failed service calls. Both user groups belong to the same business role, and backend transactions work fine for everyone.
The real root cause.
The failure is caused by inconsistent authorization resolution across Fiori layers. 1. Fiori requires authorizations at multiple levels: front-end, gateway, and backend. 2. User roles were copied or derived incorrectly during migration. 3. Authorization buffers are inconsistent across application servers. 4. Some users retain legacy GUI-focused roles not designed for Fiori.
Why this is a migration-exclusive failure?
This issue emerges because migration introduces a new authorization execution path. 1. ECC authorization checks were primarily transaction-based. 2. Fiori uses catalog, group, OData, and backend checks together. 3. Roles migrated from ECC are incomplete for Fiori usage. 4. Partial role cleanup creates user-specific behavior.
The fix, the interview-winning answer.
A senior basis consultant resolves authorization issues holistically. 1. Trace failed users using /ilfant/error_log and SU53. 2. Compare front-end gateway and backend authorizations. 3. Rebuild authorization buffers across all application servers. 4. Align roles to SAP-delivered Fiori catalogs and groups. 5. Avoid copying GUI roles into Fiori environments. This answer shows understanding that Fiori authorization is multi-layered, not role-based alone.
Follow-up 1. Why does this issue affect users inconsistently?
Answer: because authorization caching and role composition differ per user and per application server.
Follow-up 2. Why doesn't SU53 always show the problem?
Answer: because SU53 captures backend failures only. Many Fiori issues occur at the gateway or front-end layer.
Follow-up 3. Curveball. Why can role regeneration worsen the issue temporarily?
Answer: because regenerating roles clears buffers and exposes missing authorizations that were previously masked.
Exclusive pro tip.
If Fiori works for one user but not another, the problem is almost never the app.
Scenario 54. Web dispatcher routing breaks after migration.
Immediately after migration, users report that Fiori URLs intermittently fail or redirect incorrectly. Some users reach the launchpad. Others receive HTTP 404 or 503 errors, and some are routed to the wrong backend system. Direct access to backend systems works, but access through Web Dispatcher is unreliable.
The real root cause.
The failure is caused by outdated or incorrect routing configuration in Web Dispatcher. 1. Backend system identifiers change during migration. 2. New Fiori and gateway services require updated routing rules. 3. Old URL patterns and host mappings were reused. 4. Load balancing groups no longer match backend reality.
Why this is a migration-exclusive failure?
This issue appears because migration fundamentally changes the system landscape. 1. ECC landscapes relied less on HTTP-based routing. 2. S/4HANA introduces mandatory Fiori and gateway paths. 3. System IDs, message servers, or host names often change. 4. Legacy Web Dispatcher configs are reused without redesign.
The fix, the interview-winning answer.
A senior basis consultant treats Web Dispatcher as part of the architecture, not a proxy. 1. Review and update all routing rules post-migration. 2. Validate backend groups against current message servers. 3. Test URL routing for all Fiori and gateway services. 4. Remove obsolete ECC-era routing entries. 5. Perform load-based routing tests under real traffic. This answer demonstrates understanding that routing is a first-class architectural component in S/4HANA.
Follow-up 1. Why does direct backend access work while web dispatcher fails?
Answer: because direct access bypasses routing logic. The failure lies in request distribution, not backend availability.
Follow-up 2. Why do routing issues appear randomly?
Answer: because different users are routed to different backend instances, exposing inconsistencies.
Follow-up 3. Curveball. Why can restarting web dispatcher temporarily hide the issue?
Answer: restarting resets routing caches, masking misconfiguration until traffic patterns reintroduce the problem.
Exclusive pro tip.
If Fiori works without web dispatcher, the problem is never Fiori.
Scenario 55. S/4 GUI works. Fiori is completely unusable.
After go live, SAP GUI transactions work normally. Users can post documents, run reports, and complete business processes using GUI. However, Fiori apps fail entirely. Launchpad access is slow or broken, tiles error out, and business leadership questions why a modern system requires falling back to SAP GUI.
The real root cause.
The failure is caused by treating Fiori as optional rather than mandatory infrastructure. 1. Backend ABAP system is healthy and accessible via SAP GUI. 2. Fiori frontend gateway or HTTP infrastructure is misconfigured or incomplete. 3. Migration planning prioritized technical conversion over user access architecture. 4. Fiori dependencies were validated late or not at all.
Why this is a migration-exclusive failure?
This failure appears because ECC did not require browser-based access for core functionality. 1. ECC users relied almost entirely on SAP GUI. 2. S/4HANA mandates Fiori for many core business processes. 3. Migration often validates backend first, frontend later. 4. Fiori failure is perceived as system failure, not UI failure.
The fix, the interview-winning answer.
A senior basis consultant treats Fiori availability as a go-live blocker. 1. Validate Fiori landscape readiness before cutover. 2. Ensure gateway, ICAM, and HTTP services are fully operational. 3. Confirm front-end back-end connectivity and trust configuration. 4. Test mandatory Fiori apps used by business roles. 5. Do not declare go live until Fiori is stable. This answer demonstrates understanding that S/4HANA without Fiori is functionally incomplete.
Follow-up 1. Why do teams accept GUI working as sufficient initially?
Answer: because GUI success gives a false sense of system readiness, especially to technical teams familiar with ECC.
Follow-up 2. Why is business impact higher when Fiori fails?
Answer: because many S/4HANA processes are designed assuming Fiori access, not GUI fallback.
Follow-up 3. Curveball. Why can fixing Fiori late damage leadership confidence?
Answer: because leadership perceives front-end failure as architectural immaturity, not a fixable configuration issue.
Exclusive pro tip.
If business leaders fall back to GUI, you have already lost the migration narrative.
Scenario 56. Post-go-live browser cache issues masquerading as system failures.
Immediately after go-live, users report inconsistent Fiori behavior. Some apps fail to load, others show outdated UI, and some work only after multiple refreshes. Different users report different symptoms, even when using the same app. Basis teams initially suspect gateway or backend instability.
The real root cause.
The failure is caused by stale browser-side and intermediate cache artifacts. 1. Fiori UI resources are aggressively cached by browsers. 2. Old UI versions conflict with newly deployed backend services. 3. Reverse proxies and web dispatcher may cache outdated responses. 4. Users carry cache across system refreshes and transports.
Why this is a migration-exclusive failure?
Migration introduces massive UI and service changes simultaneously. 1. ECC rarely relied on browser-based UI execution. 2. S/4HANA Fiori deploys large UI5 resource updates at once. 3. Post-migration transports invalidate cached front-end assets. 4. User devices become part of the runtime landscape.
The fix, the interview-winning answer.
A senior basis consultant treats browser cache as a production dependency. 1. Communicate mandatory cache clearing steps to users. 2. Use cache buster parameters and UI5 cache reset tools. 3. Invalidate web dispatcher and proxy caches post-go live. 4. Standardize browser versions for business users. 5. Confirm UI behavior after cache reset before deeper analysis. This answer demonstrates awareness that modern SAP landscapes extend beyond the server boundary.
Follow-up 1. Why does clearing cache fix so many Fiori issues?
Answer: because it forces the browser to load the correct UI and service metadata instead of outdated assets.
Follow-up 2. Why do basis teams often misdiagnose this initially?
Answer: because symptoms resemble backend failures, and browser behavior is outside traditional basis focus.
Follow-up 3. Curveball. Why can cache issues disappear and reappear unpredictably?
Answer: because browser cache expiration, user behavior, and proxy refresh cycles vary across environments.
Exclusive pro tip.
If the issue fixes itself after refresh, suspect cache before architecture.
Scenario 57. HTTPS/certificate mismatches breaking Fiori access.
After migration, users are unable to access Fiori over HTTPS. Browsers display security warnings, blank screens, or blocked content messages. In some cases, the launchpad loads partially, but apps fail due to mixed content errors. SAP GUI access works, leading teams to assume the system is healthy.
The real root cause.
The failure is caused by certificate and trust misalignment across HTTPS layers. 1. Certificates were regenerated or replaced during migration. 2. Front-end gateway and back-end systems use inconsistent certificate chains. 3. Subject alternative names and do not match accessed host names. 4. Mixed HTTP or HTTPS references exist in services or destinations.
Why this is a migration-exclusive failure?
Migration forces HTTPS to become mandatory rather than optional. 1. ECC environments often tolerated HTTP or self-signed certificates. 2. S/4HANA Fiori enforces strict browser security policies. 3. System host names and URLs often change during migration. 4. Legacy trust configurations are not automatically upgraded.
The fix, the interview-winning answer.
A senior basis consultant treats certificate alignment as a core architecture task. 1. Standardize HTTPS usage across all Fiori-related components. 2. Validate certificate chains and send entries for all accessed URLs. 3. Import root and intermediate certificates consistently. 4. Eliminate mixed content references in services and destinations. 5. Test Fiori access using production-equivalent browser security settings. This answer demonstrates understanding that browser trust is now part of SAP system design.
Follow-up 1. Why does SAP GUI work even when HTTPS fails?
Answer: because SAP GUI does not enforce browser-level HTTPS and certificate validation rules.
Follow-up 2. Why do some browsers fail while others work?
Answer: different browsers enforce HTTPS and certificate policies with varying strictness.
Follow-up 3. Curveball. Why can certificates appear valid but still break Fiori?
Answer: because validity does not guarantee trust. Missing intermediates or SAN mismatches still cause failures.
Exclusive pro tip.
If Fiori fails only in modern browsers, always suspect certificates first.
Scenario 58. Backend is fast, Fiori is slow, why?
After migration, performance testing shows that backend transactions execute quickly in SAP GUI. However, the same business process executed through Fiori feels slow. Tiles take time to open, list reports load gradually, and users complain about latency despite HANA showing low response times.
The real root cause.
The failure is caused by latency accumulation across multiple front-end and middleware layers. 1. Fiori requests pass through browser, web dispatcher, gateway, and backend. 2. Multiple OData calls are triggered for a single app launch. 3. Network latency and SSL handshakes add overhead. 4. Front-end rendering time is often mistaken for back-end slowness.
Why this is a migration-exclusive failure?
Migration introduces a distributed execution model that did not exist in ECC. 1. ECC GUI communicated directly with the application server. 2. S/4HANA Fiori uses stateless HTTP calls and UI rendering. 3. Performance tools focus on back-end response, not end-user experience. 4. Latency becomes visible only after real user adoption.
The fix, the interview-winning answer.
A senior basis consultant diagnoses performance end-to-end, not server by server. 1. Measure response time across browser, gateway, and backend. 2. Analyze number and sequence of OData calls per app. 3. Optimize web dispatcher and network configuration. 4. Enable HTTP keep alive and SSL session reuse. 5. Tune front-end cache and UI5 resource loading. This answer shows understanding that user-perceived performance is the true success metric.
Follow-up 1. Why does SD03 show good response times while users complain?
Answer: because SD03 measures backend dialog time, not browser rendering or network latency.
Follow-up 2. Why does performance improve during off-hours?
Answer: lower network congestion and reduced parallel load reduce cumulative latency.
Follow-up 3. Curveball. Why can adding more app servers make Fiori slower?
Answer: because additional hops and session distribution increase coordination and cache misses.
Exclusive pro tip.
If the backend is fast and Fiori is slow, the problem is almost never HANA.
Scenario 59. OData services timeout only under load.
During initial testing, all Fiori apps work as expected. After go live, as user volume increases, specific apps start timing out. The same OData services respond correctly when tested individually, but fail intermittently during peak business hours. Outside peak load, the problem disappears completely.
The real root cause.
The failure is caused by concurrency pressure across gateway, ICOM, and backend processing layers. 1. OData services are stateless and executed in parallel under load. 2. Gateway work processes become saturated before backend dialog processes. 3. ICM and HTTP thread limits are reached faster than expected. 4. Backend services were never stress-tested with realistic concurrency.
Why this is a migration-exclusive failure.
Migration introduces massive parallel access patterns that did not exist in ECC. 1. ECC GUI traffic was largely sequential per user. 2. Fiori triggers multiple simultaneous OData calls per user action. 3. Concurrency grows exponentially with user count. 4. Traditional load tests focus on backend dialog, not gateway saturation.
The fix, the interview-winning answer.
A senior basis consultant tunes the system for concurrency, not just speed. 1. Increase gateway and ICM work process capacity appropriately. 2. Review and tune HTTP timeouts and thread limits. 3. Analyze OData service execution time under load. 4. Reduce unnecessary parallel OData calls where possible. 5. Validate performance during peak business concurrency. This answer demonstrates understanding that modern SAP systems fail under load, not logic.
Follow-up 1. Why do OData services work fine when tested individually?
Answer: because individual tests do not replicate concurrency. The failure is caused by simultaneous execution, not service logic.
Follow-up 2. Why doesn't increasing backend dialog work processes fix this?
Answer: because the bottleneck often sits in gateway or ICM layers, not in backend dialog processing.
Follow-up 3. Curveball. Why can timeouts increase even when CPU usage is low?
Answer: because thread exhaustion and queuing delays can occur long before CPU saturation.
Exclusive pro tip.
If failures appear only under load, always suspect concurrency limits before code.
Scenario 60. Fiori authorization issues despite SAP_all.
After migration, Basis assigns SAP_all to affected users to rule out authorization issues. SAP GUI transactions work perfectly. However, Fiori apps still fail to open, show empty tiles, or return authorization errors. This confuses teams because SAP_all traditionally bypassed most authorization problems in ECC.
The real root cause.
The failure is caused by Fiori-specific authorization layers that SAP_all does not fully cover. 1. Fiori relies on OData service authorizations. 2. ICF service activation and SICF authorization checks apply. 3. Catalogs and groups require separate role assignments. 4. Front-end and back-end authorization checks are decoupled.
Why this is a migration-exclusive failure.
Migration introduces an authorization model that did not exist in ECC. 1. ECC relied primarily on transaction-based authorization checks. 2. S4 HANA Fiori introduces role-based UI access layers. 3. Front-end catalogs and back-end services must align. 4. SAP_all no longer represents full access across all layers.
The fix, the interview-winning answer.
A senior basis consultant understands that SAP_all is no longer sufficient. 1. Assign correct business roles containing Fiori catalogs and groups. 2. Ensure required OData services are authorized and activated. 3. Verify SIC service authorization independently. 4. Align front-end and back-end role assignments. 5. Validate access using Fiori authorization trace tools. This answer demonstrates mastery of the modern SAP authorization stack.
Follow-up 1. Why does SAP_all work for GUI but not Fiori?
Answer: because SAP_all does not include Fiori catalogs, groups, or OData service permissions.
Follow-up 2. Why do some tiles appear but fail to launch?
Answer: tile visibility and app execution are controlled by different authorization layers.
Follow-up 3. Curveball. Why is assigning SAP_all considered dangerous in S4 HANA?
Answer: because it masks missing role design and creates a false sense of system readiness.
Exclusive pro tip.
If SAP_all doesn't fix Fiori, stop assigning roles and start tracing authorizations.
Category 12 complete. When the system works but confidence doesn't.
The previous category exposed failures that occur after technical stabilization. At this point, the system may be running, jobs may be finishing, and performance may look acceptable. Yet something far more dangerous begins to surface: loss of trust. These are the moments when business users stop believing the system, even if the root cause is no longer purely technical.
The final layer, where migrations quietly fail.
The next category is not about dumps, errors, or outages. It is about perception, ownership, and timing. These failures rarely appear in project plans or test scripts, yet they define whether a migration is remembered as a success or a failure.
Please check description or comment section of this video. I have given a lot of links for downloading 8 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, system design, most asked implementation project-related questions and answers, support project-related questions and answers. Required for your SAP technical modules interviews jobs like SAP Basis admin jobs, SAP S4 HANA consultant jobs, SAP ABAP developer jobs, SAP ABAP OData developer jobs, SAP Fiori UE5 developer jobs, SAP ABAP HR consultant jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section, these questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 8 PDFs in a single zip file from below given links.
Category 13. Final reality check scenarios.
This category captures what happens when technical issues intersect with human expectations. These scenarios are not solved by patches alone. They require architectural maturity, communication clarity, and decisive ownership. Most migrations that fail reputationally fail here.
Category 13 Scenarios.
These scenarios represent the point where technical success no longer guarantees business acceptance. 61. ECC never did this, but S/4HANA does. 62. Technically live does not mean business ready. 63. Fixing one issue reveals 3 others. 64. Support tickets without clear ownership. 65. Root cause identified too late. 66. Migration succeeds, trust is lost if these scenarios are mishandled. The migration is remembered as a failure, even when the system is stable.
Scenario 61. ECC never did this, but S/4HANA does.
After go live, business users repeatedly report issues with the same explanation. ECC never behaved like this. The system is technically correct, data is consistent, and no errors are visible. Yet user confidence erodes as familiar processes now behave differently under S/4HANA.
The real root cause.
The failure is caused by a mismatch between technical correctness and user expectations. 1. Runtime behavior has changed due to parallel execution. 2. Timing and sequencing assumptions no longer hold. 3. S/4HANA enforces stricter data and process consistency. 4. User habits were formed under ECC limitations.
Why this is a migration-exclusive failure.
Only migration exposes this expectation gap. 1. Users compare behavior directly with the legacy system. 2. Technical improvements feel like regressions to end users. 3. Process changes are subtle but impactful. 4. No amount of technical stability fixes perception issues.
The fix, the interview-winning answer.
A senior consultant manages expectations, not just systems. 1. Acknowledge behavioral differences explicitly. 2. Explain why S/4HANA behaves differently. 3. Distinguish defects from design changes. 4. Update user training and documentation. 5. Protect trust by communicating early and clearly. This answer demonstrates understanding that migration success is as much psychological as technical.
Follow-up 1. Why do users resist technically correct behavior?
Answer: because correctness does not equal familiarity. Users value predictability more than internal consistency.
Follow-up 2. Why can't we just say this is how S/4 works?
Answer: that response dismisses user impact. Migration requires empathy and explanation, not authority.
Follow-up 3. Curveball. Why can fixing these issues increase user distrust?
Answer: frequent changes reinforce the perception that the system is unstable, even when fixes are correct.
Exclusive pro tip.
Users remember how a system feels, not how it is designed.
Scenario 62. Technically live does not mean business ready.
The system passes all technical checks. SUM completed successfully, transports are clean, interfaces are connected, and monitoring shows green. Leadership announces go live. Within hours, business users report delays, confusion, and inability to complete critical end-to-end processes. The system is live, but the business is not.
The real root cause.
The failure is caused by equating technical completion with operational readiness. 1. Technical validation focuses on system health, not business flow. 2. End-to-end scenarios are not fully exercised under real conditions. 3. User readiness and process timing are underestimated. 4. Go-live decisions prioritize milestones over usability.
Why this is a migration-exclusive failure.
Migration compresses years of change into a single event. 1. Entire business processes shift simultaneously. 2. Legacy workarounds no longer exist. 3. Parallel execution changes process timing. 4. Small usability gaps multiply across departments.
The fix, the interview-winning answer.
A senior consultant defines go-live readiness beyond technical success. 1. Validate critical business scenarios end-to-end. 2. Test under realistic load and timing conditions. 3. Include business users in final readiness sign-off. 4. Define clear hypercare success criteria. 5. Delay go-live if business readiness is not proven. This answer shows maturity in protecting business continuity over project optics.
Follow-up 1. Why do technical checks fail to reflect business readiness?
Answer: because they measure system capability, not human interaction, process sequencing, or operational timing.
Follow-up 2. Why is this gap often ignored before go-live?
Answer: because technical milestones are visible and measurable, while business readiness is harder to quantify.
Follow-up 3, curveball. Why can delaying go-live actually reduce project risk?
Answer: because controlled delay preserves trust and avoids operational chaos that takes months to repair.
Exclusive pro tip.
A system can be technically perfect and still operationally unusable.
Scenario 63. Fixing one issue reveals 3 others.
After go-live, a critical issue is identified and fixed quickly. The fix is technically correct and resolves the original problem. However, shortly after deploying the fix, multiple new issues appear in different areas of the system. The support team enters a cycle of constant firefighting.
The real root cause.
The failure is caused by interacting changes within a tightly coupled system. 1. Migration alters execution order and timing across components. 2. Fixes address symptoms without full system impact analysis. 3. Hidden dependencies surface only under production load. 4. Changes ripple through previously stable processes.
Why this is a migration-exclusive failure.
Migration creates an environment where cause and effect are decoupled. 1. Legacy assumptions no longer hold true. 2. Parallel processing increases interaction complexity. 3. Baseline behavior is still evolving post-go-live. 4. Small fixes can have disproportionate impact.
The fix, the interview-winning answer.
A senior consultant stabilizes the system before optimizing it. 1. Establish a controlled fix deployment process. 2. Analyze cross-process impact before applying changes. 3. Limit concurrent fixes during hypercare. 4. Monitor system behavior after each fix. 5. Treat cascading issues as systemic signals. This answer shows discipline in restoring stability before pursuing perfection.
Follow-up 1. Why do fixes cascade after migration?
Answer: because migration changes execution dynamics. Fixes interact with altered timing, data flow, and parallelism.
Follow-up 2. Why didn't testing reveal these dependencies?
Answer: testing environments rarely replicate full production load and concurrency, masking interaction effects.
Follow-up 3. Curveball. Why can fixing fewer issues lead to faster stabilization?
Answer: because reducing change allows system behavior to settle, making true root causes easier to isolate.
Exclusive pro tip.
During hypercare, stability is more valuable than speed.
Scenario 64. Support tickets without clear ownership.
After go-live, the support ticket volume increases rapidly. Issues are logged across multiple queues: basis, ABAP, functional, security, and interfaces. Each team investigates within its own scope, but tickets keep getting reassigned. Resolution time increases and business frustration escalates.
The real root cause.
The failure is caused by fragmented ownership in the post-migration support model. 1. Support responsibilities are divided by technical domain. 2. End-to-end issue ownership is missing. 3. Symptoms are investigated instead of root causes. 4. Tickets move between teams without resolution.
Why this is a migration-exclusive failure?
Migration introduces issues that span multiple domains simultaneously. 1. Single incidents involve basis, ABAP, and functional layers. 2. Legacy support models assume isolated problem domains. 3. Migration issues blur traditional ownership boundaries. 4. Standard escalation paths become ineffective.
The fix, the interview-winning answer.
A senior consultant restructures support around outcomes, not components. 1. Assign a single owner per incident regardless of domain. 2. Define clear escalation and decision authority. 3. Track issues from symptom to root cause. 4. Create cross-functional hypercare teams. 5. Measure resolution effectiveness, not ticket closure. This answer demonstrates leadership in restoring trust through accountability.
Follow-up 1. Why do domain-based queues fail after migration?
Answer: because migration issues rarely stay within one domain. Domain queues fragment responsibility instead of solving problems.
Follow-up 2. Why doesn't escalation automatically fix ownership?
Answer: escalation increases visibility, not clarity. Without defined ownership, issues still bounce between teams.
Follow-up 3. Curveball. Why can faster ticket closure worsen user trust?
Answer: closing tickets without solving root causes creates recurring issues, making users feel ignored rather than supported.
Exclusive pro tip.
Ownership resolves issues faster than expertise alone.
Scenario 65. Root cause identified too late.
After weeks of firefighting, war rooms, and emergency fixes, the team finally identifies the true root cause of repeated issues. Unfortunately, by the time the correct diagnosis is made, business disruption has already occurred, confidence is damaged, and temporary workarounds have become permanent.
The real root cause.
The failure is caused by delayed root cause analysis under pressure. 1. Teams focus on symptom removal instead of diagnosis. 2. Parallel issues obscure the original failure point. 3. Temporary fixes mask underlying structural problems. 4. Decision-making prioritizes speed over correctness.
Why this is a migration-exclusive failure.
Migration environments distort cause and effect relationships. 1. Multiple system changes go live simultaneously. 2. Baseline behavior is unknown immediately after cutover. 3. Legacy assumptions interfere with diagnosis. 4. Pressure to stabilize suppresses deep investigation.
The fix, the interview-winning answer.
A senior consultant enforces disciplined diagnosis even under pressure. 1. Pause cascading fixes to observe system behavior. 2. Establish a single source of truth for incidents. 3. Correlate issues across technical and business layers. 4. Protect time for structured root cause analysis. 5. Treat delayed diagnosis as a governance failure. This answer demonstrates restraint and judgment during high-pressure stabilization.
Follow-up 1. Why is root cause analysis delayed after go-live?
Answer: because urgency drives reactive behavior. Teams fix what is visible instead of what is fundamental.
Follow-up 2. Why don't standard troubleshooting methods work well here?
Answer: they assume stable baselines. Migration environments lack stable reference behavior.
Follow-up 3. Curveball. Why can early diagnosis feel riskier than quick fixes?
Answer: because it requires admitting uncertainty and delaying visible action, which can feel politically unsafe.
Exclusive pro tip.
The longer you wait to diagnose, the harder truth becomes to accept.
Scenario 66. Migration succeeds, trust is lost.
From a project perspective, the migration is declared a success. The system is live, data is consistent, and critical defects are resolved. However, months later, business users still hesitate to rely on the system. Workarounds persist, shadow systems emerge, and confidence never fully returns.
The real root cause.
The failure is caused by cumulative erosion of confidence during migration. 1. Repeated disruptions during early usage phases. 2. Inconsistent behavior compared to legacy expectations. 3. Delayed resolution of critical business-impacting issues. 4. Perception that stability was prioritized over usability.
Why this is a migration-exclusive failure.
Only migration combines technical change with emotional disruption. 1. Users are forced to abandon familiar processes. 2. Early negative experiences anchor long-term perception. 3. Technical success is evaluated through business pain. 4. Trust, once lost, is difficult to rebuild.
The fix, the interview-winning answer.
A senior consultant treats trust as a deliverable, not a byproduct. 1. Stabilize the system before introducing enhancements. 2. Resolve high-impact issues visibly and decisively. 3. Communicate transparently about known limitations. 4. Involve business users in recovery milestones. 5. Measure success through adoption, not uptime. This answer demonstrates understanding that migration success is defined by confidence, not completion.
Follow-up 1. Why doesn't stability automatically restore trust?
Answer: because trust is based on experience, not metrics. Users remember disruption longer than recovery.
Follow-up 2. Why do users create workarounds even after fixes?
Answer: workarounds provide perceived control. Once adopted, they feel safer than relying on the system again.
Follow-up 3. Curveball. Why can optimization efforts backfire at this stage?
Answer: users interpret change as instability. Optimization without trust feels like risk, not improvement.
Exclusive pro tip.
You don't earn trust by fixing systems. You earn it by protecting users.
Here is the bonus scenario. The system is fast, stable, and still rejected by the business.
After go-live, all technical checks are green. HANA memory is stable, CPU is low, dumps are 0, jobs finish on time, and Fiori responds. Yet users complain that the system feels slow, unreliable, and worse than ECC. Leadership escalates not because of outages, but because confidence is collapsing.
The real root cause.
The failure is caused by a mismatch between technical success metrics and human perception. 1. ECC users were conditioned to synchronous, blocking behavior. 2. S/4HANA introduces asynchronous execution patterns. 3. Fiori shows partial data early instead of blocking. 4. Users interpret asynchronous behavior as instability.
Why this is a migration-exclusive failure.
This problem does not exist before migration. 1. ECC trained users to wait for the system. 2. S/4HANA trains the system to respond immediately. 3. Asynchronous updates break old trust models. 4. Users equate determinism with reliability.
The fix, the interview-winning answer.
A senior consultant fixes perception before touching performance. 1. Educate business users on asynchronous behavior changes. 2. Align UX expectations during UAT, not post-go live. 3. Identify async processes and communicate delay boundaries. 4. Avoid overtuning a system that is already healthy. 5. Treat user confidence as a production dependency. This answer proves you understand that migrations fail psychologically before they fail technically.
Follow-up 1. Why does this issue never show up in testing?
Answer: because test users focus on correctness, not trust. Perception issues emerge only under real business pressure.
Follow-up 2. Why does adding hardware never fix this?
Answer: because the problem is not speed. It is expectation mismatch.
Follow-up 3. Curveball. Why do senior users complain more than junior users?
Answer: because senior users built muscle memory on ECC behavior. Juniors adapt faster.
Exclusive pro tip.
If users say the system feels unreliable but logs are clean, stop tuning and start explaining.
Category 13 complete. The truth nobody prepares you for.
These final scenarios are not about broken systems. They are about broken confidence. At this stage, most migrations have already succeeded technically. Yet users are frustrated, leadership is impatient, and support teams are overwhelmed. This is where migrations are judged, not by logs or metrics, but by trust. Senior basis consultants recognize that technical excellence alone is no longer enough here.
The real meaning of an ECC to S/4HANA migration.
An ECC to S/4HANA migration is not a technical upgrade. It is a behavioral shift for systems, teams, and organizations. Every scenario in this video exists because assumptions from the ECC world silently break under S/4HANA. The consultants who succeed are not the ones who know the most transactions, but the ones who understand where reality diverges from expectation.
Before you leave,
If this video changed how you think about S/4HANA migrations, save it. Revisit it before your next cutover. Share it with your project team. This is not content you consume once. It is a reference you come back to. If you want more scenario-driven, real production knowledge that you will not find in SAP notes or official guides, subscribe. This channel exists for consultants who want to be remembered as the ones who saw problems before they happened.
Please check description or comment section of this video. I have given a lot of links for downloading 8 PDFs in a single zip file, containing all types of most asked interview question and answers like scenario-based, technical-based, behavioral-based, real-world problem-solving, generally most asked, system design, most asked implementation project-related questions and answers, support project-related questions and answers. Required for your SAP technical modules interviews jobs like SAP Basis admin jobs, SAP S/4HANA consultant jobs, SAP ABAP developer jobs, SAP ABAP OData developer jobs, SAP Fiori UE5 developer jobs, SAP ABAP HR consultant jobs, etc., etc. These questions and answers are carefully curated by industry experts, saving you people hours of research and ensuring you people will have the most accurate and relevant answers. This PDFs includes scenario-based questions and answers, real-world problem solving, interview questions and answers where almost 80% of the people are failing to answer, system design questions and answers where almost 90% of the people are failing to answer, with detailed solutions, which are often missing from free online resources. A lot of people are claiming that these questions are coming in real interviews. So, grab them as soon as possible with both hands. Since these questions and answers covers basic to advanced interview questions and answers, that's why given 50 question and answers for each section. These questions and answers will be helpful for freshers, 2 to 3 years experienced people, and 5 or above years experienced people. Also for your interviews, you people can download all 8 PDFs in a single zip file from below given links. For more exciting tips, tricks, and more importantly, for valuable insights of interviews, please share, like, and subscribe to my channel. It has a lot of valuable information about various insights of interviews. It has a wide range of real-world portfolio projects of various technologies for interviews, and it has wide range of most asked interview questions and answers of various technologies like data science, SAP, AWS, DevOps, and full-stack web development, and more. That will be useful during interviews. It has a wide range of most asked interview questions and answers and real-world portfolio projects of various technologies for freshers, for 2 to 3 years, experienced candidates, and for 5 or above years, experienced candidates to test their skills by knowing most asked interview questions and make themselves ready for interviews.